penso che potete disattivare il video, perché vi vediamo comunque. Se non serve. Ok, grazie. Sì. We are online. Okay, okay, we can see. Everything okay. You can hear me better? Mi senti, Damiano? Mi senti chiaro? Ok, ok, va bene. Rimaniamo così allora. Fammi provare anche l'altro microfono invece, mi senti? Mi senti così? Pronto? Ok, perfetto. Va benissimo. Ok, perfetto, grazie. Sì, tra poco, sì. D'accordo, nel caso ti chiamo su Telegram, ok, grazie. In the opening, we will use this microphone, okay? Because not to switch.
Yes. So you will put here. Okay, when the audience will need a question, I will put this one.
The problem.
First, I will be here, so
dovresti sentire adesso. Mi senti? Mi senti ora? Ok, fammi provare. Aspetta, chiudo Telegram. Aspetta. Can you hear me, Damiano? Hello, Damiano? It's a test. Can you hear me?
Honorable Vice President of National Assembly of Armenia, respected President of National Academy of Sciences of Republic of Armenia, Honorable Deputy Minister of Foreign Affairs of Republic of Armenia, Honorable Deputy Minister of High-Tech Ministry of Republic of Armenia, Your Excellencies Ambassadors of Italy and India, distinguished guests, friends and colleagues. On behalf of the organizing committee, I am delighted to welcome all of you in Zeldovich meeting in Yerevan. As you know, Zeldovich meetings are organized by ICRANet every 3 years, and which is a unique platform where the recent discoveries made in relativistic astrophysics are presented and discussed. This year's meeting holds particular significance. Over 100 distinguished scientists from different countries are attending the meeting, and the most recent results from the currently leading experiment and satellite and Sputnik will be presented and discussed during this meeting. We will also transmit the presentation online, so everyone in the world can follow this meeting. This means that this week, Yerevan will become a very special place where the most recent discoveries of astrophysics will be presented and discussed. We are particularly happy to host the meeting this year because this coincides with the 80th anniversary of our National Academy of Sciences. So this event also is to honor this significant achievement of our academy. So over the past 18 years, our academy promoted and carried out the fundamental and applied research in different fields of science, and the scale of its academic achievement truly speaks for itself. We extend our warm congratulations to our academy, and we wish the new academic achievement in the next 80 years. So now it's my pleasure to give the floor to His Excellency Mr. Akop Arshakian, the Vice President of the National Assembly, for the opening remarks and welcome.
Good morning, ladies and gentlemen, Your Excellencies, Ambassadors, Italy and India, my colleagues from the government, of course, the different honorable guests, remotely, who is here today and working already 20 years with Armenia. It is our pleasure to have you here. And Alex Alakan, the local representative of ICRANet. Your efforts are very important to Armenia. Your colleagues, scientists, enthusiasts, compatriots, and international guests, I hope that you enjoy today's event. And Armenia pays a big attention on science, scientific development, and also technology. If we
talk about the history. Many people know that Armenia has a rich history in science, scientific discovery, especially astrophysics, mathematics, physics, and of course it is a great pleasure to serve the humanity, international community, people of Armenia, and of course our friends all over the world, discovering many scientific achievements in Armenia. However, we know exactly that it is impossible to reach any success without international cooperation. And recently, in our governmental budget, the budget for science was doubled for the recent couple of years, and the majority, a big part of it, is dedicated for international collaboration. And there is a certain way of how to be a part of these projects with the Armenian institutions, and of course the National Academy of Sciences has a big role on this with the 40 institutions. Many of them are in technology, mathematics, physics, astrophysics, and I would like to call for partnership for the people who today visited Armenia, and I would like to also ask to be active on collaboration, because we know, everyone knows that no single country can reach big successes alone. And we should really join our efforts to move the society and the industry to serve better the human kind. I would like to again welcome all of you to Armenia. I would like to wish this event to be successful, and I would like to call for being more active, to be more collaborative, more open, and we can really achieve big successes all together joining our efforts. Thank you very much for the invite, and thank you for collaboration. Thank you for being here.
Thank you very much, Mr. Dasha, for participating on our organization and for understanding your participation. We really hope that your help to expand that with your ICRANet in Armenia and soon the legal country. Thank you very much. So, pleasure to invite the Excellency about the organization, Minister of Foreign Ministry, for his opening speech and remarks.
Good morning, everyone. The Honorable Jacob Arshakyan, dear Professor Bufini, dear Mr. Tarian, dear colleagues, dear participants to this international conference. And I'm pleased to welcome the participants of the Fifth Zeldovich meeting, an international conference dedicated to modern, if not ongoing, achievements in astrophysics and related fields. Of great importance for us that this year the conference is taking place in Armenia and is held by ICRANet's Armenia Center in Yerevan. I would like also to thank the director of the Center, Mr. Sakyan, for his tireless efforts in organizing and making all necessary arrangements for this conference. ICRANet is a reputable and inclusive platform for international cooperation in the field of relativistic astrophysics, which brings together the government, scientific institutions, and universities. As a founding member of ICRANet, Armenia has been actively engaged in cooperation with partner countries and scientific centers within the framework of this organization. Hosting such a prestigious international event in Armenia is important not only in terms of advancing cooperation between Armenia and ICRANet, but also for contributing to the further development of astrophysics in our country, establishment of new scientific partnerships, development and implementation of cooperation programs. During the conference, more than 100 renowned scientists from various countries of the world will be present, and they will present their latest accomplishments in modern astrophysics, which we have been that there's great news ahead of us throughout this conference. So, in conclusion, I would like to express the support of the Ministry of Foreign Affairs of Armenia to ICRANet in strengthening its capacities and international partnerships. I wish success to all participants of the conference and looking forward for your deliberations. I thank you.
Thank you very much, Mr. Yerevan. And since 2015, we started our colleague in Armenia. We always keep strong support of our foreign ministry, and we are very thankful for it. And without this support, we cannot even succeed in Armenia. So once more, thank you very much for your support in the matter. Thank you very much. And I would like to thank our Italian ambassador, because we always feel this support for our activities for Ukraine. Thank you very much. Now I would like to invite Professor Lupini, the director of ICRANet, for his virtual speech, because all of this would be possible without the strong effort of Professor Lupini in the past 20 years. So we have collaborated with Armenia in 20 years.
Well, it is indeed a great pleasure to be here, but also a moment, believe me, of great responsibility, which we share the historical moment with some of the 100 scientists who are coming from all over the world from this event. And each one has a significant part in this history. Why Armenia? Let me dream a moment and go back to mythology, or everybody knows that there was, or at least is thought to have existed, a great delusion. But also everybody knows that there was something starting new in Novae Arch, in Armenia and Arab. This is the spirit. It's no mystery that we are living in a very, very complex moment in the history of mankind, which has no precedent. Like the great solution, but the hope is to lead the way that there is the new, completely new, completely unexpected, which is based. And one question was how sure we are that we are in the right track. And my answer is we are in the right track because we are guided by the idea. The thought of Albert Einstein. How can I show you practically? Yes. The key is the black hole. The black hole. I invented the name with John Wheeler many years ago, 51 years ago. What is a black hole? You see, this is an Italian artist, cartoon, of this object. There is no up, down. The black hole is here at the center. And the big problem is this arc, or is just silent. There was a long debate when this was casted. The artists had to follow the geodesic, the equation of Einstein carefully. Is this art or is just the technology? There was a big discussion which was followed by the professor of my wife in Rome asking an opinion. He said, you have to follow the Einstein equation to see this. These are the trajectories of the particle around the black hole, which is here. He has no freedom to choose. You have to follow that. Is this art? And this man said, this big knowledge of art in Italy at Gam said, let's look at it. It's beautiful. The word is art. It's not only art. It's the sea. And then you can see this like that, like that, like that. There is not like in a statue up and down. It's only the action. And every 3 years, we give in the Grossman meeting this award to some of the leading institutions in the world. In this special case, I brought this because it was attributed to IC, the space agency of Russia, which launched with Germany the Aerosita, and we will hear the talk by the representative of Yerevan later on in the lecture. And he will bring this in the ET center back where it belongs to. Hoping for a new era. Why? This comes from Einstein equation. Why are we so excited? Why? So excited because the sun emits 10 to the 33 Earth per second. It's a unit. If you take the star like the sun in our galaxy, there are 100 billion of objects like the sun. If you sum the energy of the sun of 100 billion, you obtain not 10 to the 33, but you obtain 10 to the 45. Well, it's a huge energy, the energy of all the stars of the galaxy emit. But what we are witnessing today, and here first evidence in this meeting, that there is an object which is not only 10 to the 45 Earth per second, but it emits up to 10 to the 54 Earth per second. What it means? The energy, not of star, not of the star, of all the stars of the galaxy, but the number of galaxies in the entire universe. In a few seconds, and there is new science, completely new science. And somebody asked what it means, new science. It means that we are guided by Einstein equation. It's within Einstein equation which have the framework in which to make this discovery. The framework is there, is Einstein equation. But the discovery has been possible thanks to the mission Rosita from German-Russian collaboration, thanks to of course, the Fermi telescope from East Italy and US, thanks to the other message that we have been bringing up, but the message is new. There is new physics going on. We want to understand the equations of this new physics. And this, the fantastic thing which has been done through an effort which has materialized through a group of Chinese scientists working continuously in different roles in Lhasa, to arrive yesterday with the publication of this result being brought here for the first time. You understand? It's a new era. Therefore, it's true that we have the spirit, we have the deluge, we have a deluge, but we have a sign. We are based on Einstein equation, and we have new technology to learn. To learn that nature is much more powerful, much inscrutable, but at the same time can use this to regulate the quality of life in our universe and among ourselves. This is the message of this. I don't want to spend any more time to go in all the details. You will please follow. We have some of the greatest, we have few. And I don't know how many animals Noé brought in the ark. Well, they were fortunate to be among the ones who survived. The thing we know is that today here we have 100 scientists from all over, from India, from Italy, from Argentina, from Russia, from China, and we have the most beautiful result from China, and from US. The GRB in the year 221009A. This is the magic number. And the other magic number for us, which believe me, we really have this in our art, is 220101A. There are two objects which happened to explode last year, and only in 1 year we have been able to get the data. And the data are fantastic. There is totally new science to learn. We don't want to spend more time, just welcome all of you, and let's start to immediately, soon after, to work on all this. And of course, my thanks go to Armenia, to all the members of ICRANet, to the Italian government, for the continuous support, and for this great adventure that we are living today. We expect to fortify ourselves in this week and establish new life and hope, new collaboration and understanding. After all, if we look at this explosion happening a few more instants after the Big Bang, and being able to see and harvest that science there, I mean, we do the effort to look so far in the back, in the time, but we are harvesting the fundamental physics which we cannot do here. Therefore, this is a very exciting moment for everyone. And I thank again all the nations and politicians, and I hope very much strongly that this message, we have distinguished member, scientists from India, that also India and other countries will join ICRANet, not only with collaboration agreement like China and with joint students, but even as a member states. We have a message, a political message as well. Science can show how small is our planet, how great is the universe, how great is the understanding we can have. Let's harvest that understanding for the good will on the planet Earth. just the ceremony to bring this to Iki. Iki was an historical thing. I want to share with interact with the Relativistic Astrophysics many years ago. And clean this because it has to be there to indicate in this moment that the science can end.
Should I say a couple of words or few sentences? Yeah. Thank you, Rema. It is a very significant recognition of the contribution of SRG, spectrum and gamma, and specifically Eurosita telescope to building extreme matter of the universe, which is much more sensitive than everything that we had before, and which expands frontiers of our knowledge, understanding of actually universe. And it's a recognition, a very satisfying one, of the contribution of three institutions in Garten in Germany, and MP in Garten, MP IKI in Moscow, and Lauschkin Association in Moscow. And of course, we all are looking forward to the time, to the day, when Eurosita will wake up from its sleep mode and resume collecting X-ray photons, because every photon is a part of the legacy for science or future generations.
We already tell that this wish of waking up has been done quickly, because the next Marcel Grossman meeting, where the awards will be given again, will be next year in Beijing. And therefore, we have to be ready to now announce, let us go and walk, because the greatest result have to be ready to explain to everyone in Marcel Grossman 17 in 8-12 July next year in Beijing, which will host the MG17. Thanks to Yang Li, and in a few hours, the head of all the space mission, but not all, of some of the most important space mission of China, Nanzang, will be here with us, and we will hear from him. Somebody asked, what can we know more? Well, just wait to the conclusion up to Friday, because some of the most exciting things will happen. And in addition, we have some historical people who are participating in the memory. Koguti, here from Iran, is with us. He's a subject, and we follow his advice and his opinions in this delicate moment in the world. Everybody enjoy to speak to everyone, because we have an incredible set of people to start this new era. Thank you.
Thank you very much for the opportunity. And one more, I'd like to bring forward the guest for the ceremony. And I would like to invite all of you to continue our discussion with Republic shortly, and we can have more open discussion on the programs. Thank you very much for attending our meeting.
parlo al microfono, cioè me l'ho messo qua su... Cioè più vicino non posso, più vicino di così. Non mi vedi perché sto... Sì, sì, ma io sto qua, adesso mi vedi. Ma non mi senti? Ah. Non so come veramente... Eccolo qua, il microfono. Eccolo qua. Cioè, qua il volume è al massimo. No, no, no, al massimo, al massimo. Al massimo qua e anche al massimo al ricevitore, ma cioè, al massimo impostato sul PC. Quindi non riesco a capire perché non manda più. Sì, ma insomma, aspettavamo meglio questo. Ma guarda, io mi sento come si chiama, auricolare e mi sento benissimo. Cioè, all'auricolare che è collegato al microfono. Ma no, perché qua è al massimo, è messo al massimo. Sì. L'altro sta qua e mi avvicino pure l'altro. Mi senti? Mi senti adesso? Sì. Parlo con... Una ventina di minuti. Ma cioè, dici che si sente poco qua al microfono, quindi non vale la pena utilizzare questo qua che abbiamo portato, secondo te? Sì, vedi un attimo, sì. Però io vedo, sì, ti colleghi al PC, giusto? Fammi vedere un attimo. Sì, sì, sì, guarda, sì, vedo che l'entrata si sente bassa, sì, sul PC, però di nuovo è qualche problema con il PC perché mi sento bene. Vai, va bene, d'accordo. D'accordo, sì, sì, sta addosso, ok, vai. Allora. Я уже забыл, по-русски или по-английски? English? У нас проблема, значит, с аудио. То есть здесь аудио я слышу. То есть вот я говорю, я прекрасно себя слышу, да, на входе. А вот здесь очень слабый сигнал. Вот он сейчас пытается разобраться, но очень слабый сигнал мы получаем. Почему? Я не понимаю. Не, ну, вряд ли. Здесь специфическая, значит, конфигурация. Но я думаю, что он сейчас сделает. Ok. Vediamo se funziona così. 130%. Ok. В этом проблема.
Просто чувствительно.
Да, но вот эти, это суперчувствительные микрофоны, то есть они должны идеально работать. То есть где-то, видимо, проблема вот отсюда, вот сюда, которая приходит, вот с этой штукой. Не знаю. Окей. Okay. Okay. You hear me? Hello? Hello? Hello? Damiano? Senti meglio? Mi sembra che ha alzato un pochino. Vabbè, vai tu. Pronto? Sì. Metti 200, questo funziona. Sì, ok. Adesso sì. Ah, va bene. Ok, 150 adesso, sì. Ok. Ma forse si potrebbe alzare ancora un po'. Sì, funziona bene. Parlo a tutti e due. Sì, attaccato alla camicia, esatto. Magari ha aumentato un pochino di più, perché il livello... Sì, va bene. Lasciamolo così. Ok. D'accordo, perfetto. Ok, ti ringrazio. Come va lo streaming? Si vede tutto, tutto a posto, no? Ok, guarda, ho zoomato un pochino adesso. Sì. Ma stavo lontano, vabbè. Sì, infatti. No, vabbè, lasciamo così. Ok. Grazie. A dopo. Grazie. Okay, it's fixed, so we need for every speaker to attach this here and this here, okay? You can do that?
I will do that.
Okay.
But one more question. When they share with their own computers, it won't be visible on the Zoom.
No. Zoom is needed just for
For
remote speakers.
okay.
We have this
Okay,
there
so
for
that's good. Okay. I should put on this microphone, yeah. But when we still, yeah. your
Yours
wrist.
too.
Yes. Okay, something.
Is it on? No, it's on. Okay.
No, sorry.
No, I'm speaker.
So we remove this one, right? So this whole one.
Слабое, кстати, слабое.
Потому что да, где-то там что-то, да, отсоединяется, я заметил.
Только надо соединить с красным, да? Okey, kombinal bakalım.
Կոմպարելը որ ունենա դա HDMI, եթե չունի Type-C,
Այդ երկուսը մենան,
ես մեկը մեկը,
դելա մենը։
բայց ես ինչա։ Պետք չի գա, այս է կարող է չանի որ կլինի, որ վկայով լինի, ուրեմն իրա կաբելով դիգրաս վկա,
Şöyle de ha.
չէ, սրանց հակառակ։
Mikrofonu biraz daha da var.
Awesome. Տեսի ունենք, իսի անջատածա
Այս ամենը չէ, այս նոթբուքին է վերաբերում, ռեսիվերը դրա միացրած,
Ես էսի թողել եմ կեզ, դրանց էսի վերջում կնկալես ռեսիվերը ստեղ միացրած է, թե պետք է նիասենք կյանք չունենա, բայց ողմենի կարաս անըսպես սրան կլի մանգելաս սպանալս տոշնի
Zem
This is my glass.
I thought someone from
Sorry, thank you.
Everything is mixed today.
Esilona, audience hamara, որ հարցում են միասին yours.
Yeah.
Just after you start, I will have to leave a moment.
No problem. Will you come back to the end of my talk to stop me at time, or I can speak until lunch?
Okay? Hello, hello, hello.
Не проблема совершенно. Мне неправда, мне все равно, где сидеть, я знаю, как политики устроены. Микрофон включен, поэтому надо аккуратно говорить всякую ерунду.
Мы еще поговорим, потому что я хочу вам что-то показать, что мы сделали все уже какие-то.
Хорошо, да, отлично, да.
Նարեջան, միկրոֆոնը
Okay, we can start. It is indeed a great pleasure to have Marat Gifarov, who is one of the leading scientists who was operated at Rosita, to report, and I think we have a connection with Rashid Shulyayev sometime during the at the end of the presentation. Can we make sure that Rashid will be connected to us just at the end of Marat's presentation? At the end of Marat's presentation, we will have a short contact with Rashid Shulyayev. Okay? Therefore, we can start, and I hope and I plan to have here
Do we start, Rema? Yeah. Thank you, Rema. Thank you for inviting me here. And it's especially pleasant that this is Zeldovich meeting of the Zeldovich series of meetings, and whom I met when I was a young PhD student, even undergraduate student. Even had a chance to give a couple of talks at his Moscow astrophysical seminars. And it's also significant that I will be talking about SRG, Rosita, and he was at the early stages of the mission. He was instrumental in making this happen, in informing and shaping the mission. So not everybody here, I'm sure, most of you don't know the history of SRG. It actually has a very long history. It started in 1987, same time when I was a PhD student, and I witnessed the first meetings of international collaborations of building a very big orbital observatory, which was called Spectrum RG. Unfortunately, it didn't make it. It was canceled in 2001 when many instruments were built, like, for instance, the X-ray telescope on Swift is a JetX telescope from SRG. So it was canceled, but then a few years later, in early 2000, there were various discussions between Günther Heisinger and Rashid. And Rashid was a leader of Spectrum X Gamma since the beginning to present time. And he was also instrumental in this transition to happen, that it was not completely canceled. And there were discussions about, well, we can probably make a new mission, a new concept with the same name. And this is how the modern shape of SRG came about. And as I mentioned, Günther Heisinger was important here. He was a MPE, Max Planck Institute for Extraterrestrial Physics director at the time, and also Peter Predel, who became a PI of the telescope. And the initial design goal for the new mission was quite focused. It was aimed at detecting all massive clusters in the observable part of the universe to do cosmology. Then of course, it was clear initially, and then it realized even more and more as we were preparing for the mission. And then when we started observing that it's actually much bigger than that, and we have many aspects of science with quasars, with transients, etc., which are not less important than clusters of galaxies. So it was launched in 2019, July 13, and we went there together with German scientists. It was a big group of us, and it was very heartbreaking experience. It was when we went up, and watching it was really touching experience. So it was launched to the L2 and to the orbit around L2. This is Lagrangian 2 point of the Sun-Earth system, which is about 1.5 million away from the Earth, at a very broad orbit of a comparable size, about 1 million kilometers. It arrived there a couple of months later, and a few months later, in December 2019, it started all-sky survey. In 2022, in the end of February, by the request of the German observatory, Rosita was switched to the safe mode, sleep mode, where it didn't detect photons. However, SRG continued operations, and it operates now in the interest of the Arctic Sea telescope. This is the second telescope of the mission, hard X-ray telescope built in Russia, and they are doing fantastic things like observing galactic plane and so on. And it's very pity that Rosita couldn't be a part of this. So this is how it looked at Lavochkin Industries. I think it's about half a year before launch. We went there, and yeah, so this is Arctic Sea, which was after launch, year after launch, it was named after its creator, Mikhail Pavlinsky. So now we call it Pavlinsky Arctic Sea Telescope. And Misha, he was a driver behind this telescope. He built it, and he passed away 1 year after launch. And here is Rosita, which is a bit shorter and bigger. Right, so the main plan, the main component of the science program for SRG is all-sky survey. And it was planned, and it is still planned, to have 8 surveys during 4 years. And the surveys are done in such a way that the telescope axis, they are coaxial. They make big circle on the sky, and the rotation axis follows pointed approximately between Earth and the Sun. So as the Earth moves around the Sun, the scan plane rotates, so that in 6 months we cover full sky. And so in 4 years we make 8 all-sky surveys. And in the end, we expect to have about 2 kiloseconds average exposure time, and much deeper in the ecliptic poles. Here is the exposure map, which we got, I think this is after 1 survey. You see these are ecliptic poles, and they are much more exposed because all the scans, they cross there, and we get hundreds of kiloseconds here, and continuous coverage for the group of sources which are located there. In the end, we expect to have 25 more sensitive map, or more sensitive to everything on the sky than the previous all-sky survey conducted by Rasat in 1991. So why, you may ask, why at all you want to do an all-sky survey? I can give you several answers. The easiest answer is, well, we're living in the era of big all-sky surveys in infrared, UV, optical, even in radio there is now all-sky survey data. And X-ray, and we have many examples how great science, great advances can be done from large, massive arrays of the data, like large areas of sky. And in X-rays, there was the only one X-ray survey performed 30 years ago by Rosat, which was great at the time, and it is still great. But we want to go deeper, we want to have more detail, to be comparable in sensitivity with the modern optical and UV and radio surveys. And why X-ray is important? Because X-rays are, this is actually a very clear signature of accretion onto supermassive black hole. It's a very easy, well, easy, with certain complications, way to find accreting supermassive black holes, quasars and AGN. And it's also one of the 2 very efficient methods to detect classes of galaxies. The second is CMB, Fifth Zeldovich effect. I'll show you a couple of examples. This is an image of the sky, few by few arc minutes from SDSS. We know from other data that here is located a quasar at the redshift of 6.18, 6.2. You see nothing at the SDSS plate. It's too faint. But you see a lot of very nice sources. If you look carefully, there are spiral galaxies, there are stars, there are these galaxies, etc., but you don't see the quasar. You look at the deeper Des data, well, you see it, but it's unremarkable faint source as compared to the monsters which are shining around it. And it takes a lot of effort and special techniques to find it here. We go to X-rays. This is the same size image as SDSS image. And the quasar is the only source which was detected here in the all-sky survey by E. Rosita. There is nothing else there. And this is a manifestation of the fact that so in the optical, we have tens of thousands sources per square degree density of sources depending on the depth. And they are mostly stars and galaxies and other boring objects. Of course, many people do lots of significant, interesting science with those. But if you're interested in supermassive black holes, then, well, you have a hard time finding them. If you go to X-rays, we have, for the depth of E. Rosita all-sky survey, we have a density of about 100 sources per square degree, and most of them are supermassive black holes. We have some fraction, about 10–15% of stars, X-ray active stars, and just few galaxies which they are interesting on their own, but there are not very many there. Here is another example with a cluster of galaxies. This is a cluster of galaxies at the redshift 0.76, pretty distant for a cluster, and very massive, with a mass almost 10 to the 15 solar masses. This is an optical image obtained by RTT, Russian-Turkish telescope in Antalya. And I know people, again, the size is 5 by 5 arc minute or so. I know people who say, oh, there is definitely a cluster of galaxies here. I can't tell, whether there is one or not. But if I look at this image, X-ray image, I know immediately that there is an extended X-ray source. And this is the only source in the entire field here. And in well, you probably don't see the numbers. In about 200 seconds, we detect 160 counts from this source, and we can say it extends some rough estimation of the softness of the spectrum, etc., etc. So I hope I convinced you. These are two examples which show why is it good, why is it useful. And the goal of the eROSITA All-Sky Survey is to build a uniform because we cover full sky, and large samples of various kinds of objects, of quasars, clusters of galaxies, stars, and anything else you can think about. And we are talking large samples, meaning from 10,000, 100,000, and millions of sources. And with this, we can do many, and we are doing many exciting things. We can do cosmology with clusters of galaxies and quasars, study large-scale structure, study growth of supermassive black holes, and also, another aspect of eROSITA All-Sky Survey, we can study transients. We can look for transients, tidal disruption events, and many other interesting things. So we plan to perform 8 independent sky surveys. So far, we have 4.38, 4.5 almost. So eROSITA was built in Germany, launched by the Russian satellite, and all operations are being from Russia, and the satellite is controlled from Russia. As I said, there is a second Russian-built telescope, Arctic Sea, hard X-ray telescope. So there is an agreement between space agencies from the times they still talk to each other, that the sky is divided. There are two consortia, German and Russian. We met at Lavochkin Associations in November 2018. These are leaders of the mission and leaders of a science working group. Actually, behind this wall, there is eROSITA mounted on the platform. It's a clean room there. And the sky is divided into two halves, equal halves, where we do independent analysis, but based on the same calibration data, consistent software, consistent calibration data. And sometimes we join efforts and make something which covers full sky, as you see on one of the next slides. This is just to show you, well, it doesn't look very bright. It's much nicer on my screen, but this is full 4 sky surveys, which were done from December 2019 to December 21. And this is a partial survey, about 40% of the sky, which was done in 2022. Now, to put this in a prospect of a picture of X-ray surveys, this is a diagram which we often use. X-axis gives the area of a survey, Y-axis gives the depth from rather shallow 10 to minus 12 to fairly deep 10 to minus 16 and deeper. There is a main sequence of the surveys, and these are mostly from XMM and Chandra. It's understandable because we have some time budget for a survey. There is only so much time we are prepared to spend for the survey, so we can either do it big region of sky but shallow, or we can do a very small pencil beam survey but going very, very deep. This is where we are now with eROSITA after 4.4 surveys. We are 50, and this is where Rosat is. And this is a full sky. Of course, ideally, we want to get here. We want to cover full sky with whatever big sensitivity, large sensitivity, good sensitivity is possible. This is where Rosat was 30 years ago, and this is where we are now. We are 15 times more sensitive than Rosat. And it's not only that. We also have a few times better angular resolution, and we have significantly better energy resolution. So this is what we have, and this is really rich legacy data. I will show a few aspects of how we work with this data. This is the full sky map. Rashid will give more details. He likes talking about there are various significant structures on this map, which he will be discussing. I'll pay you attention to these white dots, like, some garbage on top of a map. But this is what I concentrate on throughout the rest of my talk. These are point sources, mostly supermassive black holes. Some of them are stars, some of them are clusters of galaxies. Before moving on, this is a team, a core team, so to say, in the Russian consortium. These are two science working groups, X-ray catalog and galaxies, quasars, and tidal disruption events working groups. And these are active people. Sergei Sazonov is my deputy in the Galaxies group. Rashid Sunyaev and Alexei Starobinsky, who is here, they are very active, and they help us. There is a saying in Russian, don't lose forest behind the trees. and you start working with specific problems, you often concentrate on trees. But there is the whole forest which you want to see, and this is what these guys help us to not to forget about. Alexander Meshcherikov, who is an expert in machine learning, neural networks, and everything. You'll see some of his results. This is a ground support group doing optical observations in Russian telescopes, and also observe in Keck, Palomar. We use ETF data, and we're starting cooperating with Spanish telescopes on Canary Islands, and there is a bunch of students. Yeah, and I should mention there are also working groups on clusters of galaxies and stars. The stars group is led by Ilfan Bikmaev and Rashid, and the clusters group is led by Eugene Churazov and also by Rashid. And I'm a member of both. So we have, let's concentrate on 4 sky surveys, which complete full sky coverage. We have, you don't see much here, but this is, was intended to be a map which shows better point sources, which is actually the whole image is covered by point sources. There is 1.5 million of X-ray sources detected at the significance level, at which we have less than 1% of false statistical fluctuations. Of course, you cannot see all the 1.5 million here. Of those, over about 250,000 are stars. They are confirmed with Gaia, proper motions, or parallaxes. There is more than 1 million of AGN and quasars. And this is, I should mention, so I should have mentioned in the beginning, I am talking about Erosit, I'm not talking about, telling about Arctic Sea, and also I'm talking about the results of a Russian consortium. So it's, in a way, it's a half of sky. You can multiply numbers by 2, and then you get the impression for the full sky. There is 23 clusters of galaxies at the level, at signal-to-noise ratio more than 5 sigma. This is where we consider reliable at the moment, but we will go down somewhat later. And also there are some sources, 5,000 approximately sources in the hard band. Many of them are Compton thick AG, and this is another direction where we're working now. So you have 1.5 million of sources. So what are you going to do it? You can publish a catalog, okay, with fluxes and coordinates, and that's it, maybe with some spectral properties. But to make any significant, meaningful science from this, you need to know 2 things. You need to know what object is this, whether it's a star, galaxy, quasar, or something else, or X-ray binary, for instance, and then you want to know distance to the source. And to do that, you have, first step would be identification. You have to find out which optical source on optical maps of Pan stars or Desilis or some dedicated observations corresponds, is a partner, is an optical source of this X-ray source. And we often have a problem of multiple matches. We have an error circle, and we have 2 or sometimes even 3 optical sources, and then we're actually having bad, difficult time trying to figure out which one is which. I'll tell about this later. So for this, we have 2 approaches. We have like 2 teams. One is machine learning methods, like we use random forest, and we also use neural networks. And this is what Sasha Meshcherikov is leading these efforts. And we also try more astrophysically motivated approaches. You'll see on the next slide. So this is an example of astrophysically motivated approach for classification, like these are galaxies, these are AGN and quasars. So this is plot like Fx to X-ray to optical ratio, and this is optical color. And you see these funny shapes here, but you can easily separate stars from extragalactic objects, for instance, using this kind of diagrams. And this is to do photometric ratios. The same we can do with neural networks. And this is an example of how the photometric redshifts using random forest algorithms. And this is some test sample. This is spectral Z with the optical spectra. And this is a photo Z measured by our random forest algorithm, which we call SRG-Z, by the way, the whole system which does this, built by Meshcherikov and his students. And you see, well, we're doing quite well. Actually, if you look at precise numbers, which I don't show here, we do better than the common results you find in the literature in terms of the RMS and catastrophic errors. Here is just one example how we found this is the most distant quasar we found in the blind search. There are more distant ones at 6.2, but there were known optical quasars where we detect X-ray emission. But this guy was found in the blind search, and this is what SRGZ predicted. This is a posteriori probability distribution. Red is the spectroscopic redshift, and this is the optical spectrum. So it works when we are lucky. Not every case is that nice, such nice as this one, but yeah, we get lucky, you know, in some good fraction of cases. Now, so we have redshifts. Then we can measure, we have X-ray fluxes. We can measure luminosity. And for AGN, we can build this kind of a histogram. This is redshift, this is luminosity. It's not the full sample. These are spectroscopically confirmed, so more reliable ones. So we see two things here. So this, it has like a shape which is constrained on both sides. So the bottom constraint is a selection effect. This is a flux-limited sample, and with the flux-limited sample, you have this characteristic shape that for a given distance or redshift, you only see sources brighter than more luminous with certain luminosity level. The shape here is physics, and first thing you see that at smaller redshifts, we have lower luminosities. And this is what is called cosmic downsizing, and it is being quantified, and we're writing papers about this. Another thing which we see, that there are very bright sources which getting 10 to 47 ergs per second. Of course, we knew that from other missions, and all these sources are blazars, actually. What we find, that sources brighter than roughly 10 to 46 are blazars, and accretion luminosity ends somewhere here, which is an interesting result. And you can also see we get all the way to 6 and beyond 6 in redshift. This is just an example. Having this, or actually we have bigger, one can start building luminosity functions, correlation functions. This is unfinished, and it's very raw preliminary plots. I don't even pay much attention to this, but you can see we can go to the redshift beyond 4. Next interesting aspect of this, of our huge AGN sample, quasar sample, is we can study large-scale structure. And having photometric redshift of sufficiently good quality, we can do three-dimensional studies. We know that universe matter is not uniform on the time on the scales of hundreds of megaparsecs, and it's called large-scale structure. And this is from Volker-Springel simulations, narrow slice in redshift, and this is what it becomes when we express it in terms of a power spectrum. And this is simulation for Rosita. Making the story short without going into all these details, well, actually, one more detail. So as we showed some years ago before launch with Gerd Hutze and Rashid Sunayev, and then continued working with Sergei Bykov, that the Rosita sample of AGN is sufficient to measure baryonic acoustic oscillations. And this illustrates how it can be done with sufficient statistical quality, but this would require spectroscopic quality redshifts for like a few million of objects. This is, in principle, I think it would be achievable on the time scale of some years, several years, 5 years, maybe a bit longer. At the moment, is not achievable. We have photometric redshifts of somewhat smaller quality, but even with this, yeah, and of course, having Bowers, we can do cosmology in a usual way. But even with having photometric redshifts, we did this exercise simulation with Sergei Bykov, my PhD student. So if we take plug-in realistic accuracy of the photometric redshifts, we can still do cosmology, because there are some, well, first of all, there is normalization slope, and there are some remaining wiggles which are left on the power spectrum, less significant than on the previous plot. And then this is an example of how we could do this. This is simulation. This is not real data yet. And, well, if you look, we can combine, it's shown for quasars and for clusters of galaxies. If we combine them together, we can reach accuracies which is in the range of 5 to 10%, which is quite reasonable. There are better accuracies in some optical surveys, but this is completely different sample, completely different systematics and everything else. Of course, once I say this, cosmology with large-scale structure, I must mention clusters of galaxies. They will be subject of Rashid's talk, so I didn't mention them at all. There are tens of thousands of clusters of galaxies we detect. But I'll just say here that, of course, also cosmology can be done from the mass function of clusters of galaxies. And in principle, well, there is a one significant difficult step when we have X-ray flux or shape parameter or temperature, and temperature is not very well defined with Eurozeta, but then going from this to the mass of the cluster, there is some assumptions involved. This is where systematics come in. If this can be overcome, as was shown Vichlinin by in some almost 20 years ago, and this is what we're walking in this direction. And given the size of a sample, like tens of thousands of clusters of galaxies, rich clusters of galaxies, of course, will be dominated by systematics. I'm getting, yeah. So it's work in progress. So my final part for a few minutes, I'll try to fit 2 or 3 minutes. My final part is about known stationary universe. We survey the whole sky every 6 months. So we go through every point on the sky once in 6 months, or some points like near ecliptic equator, we go for longer periods, and some of them, the central degree here is covered continuously. Of course, we can look at the variability of the sky at various time scales. And we do that, probably to make it quick, I say I concentrate on strongly variable objects. We see all kinds of variability, like a factor of 2, factor of 20%, or factor of 10 or 100. So when Eurozeta was operational, every 24 hours we were detecting 3 to 5 to 6 objects which changed their flux by more than 10 times compared to the previous survey. You just think about this. So half of them were stars, but half of them were AGN, confirmed, proven AGN. You can think about this. A supermassive black hole like 10 to the 8, 10 to the 9 solar masses would change its luminosity by 20 times in half a year. It doesn't fit normal accretion disk theories, but, well, apparently this is happening, and there are some ideas how this can happen. And then we have a whole range of objects which are variable, and they are mostly extragalactic. I mean, I can explain later, it's obvious from this plot. We see tidal disruption events, variable AGN, few gamma ray bursts, and so on. And we see horseless transients where we don't see anything in the optical. So I probably go a little bit faster here. So we have a catalog of 70 tidal disruption events, roughly, which is growing. Some first portion was published, and we have a mean rate of this event. And what is probably very interesting, we have three events which are associated with ice cube neutrinos. And we did this work with a group of scientists, Van Velzen, Sjoerd Van Velzen, from ZTF team, and a few other people across Europe. And so the conclusion is that some fraction of ice cube neutrinos, they are associated with tidal disruption event, with accretion flares. There are horseless, what we call horseless transients, or more scientific way to say it would be transients with an enormously high X-ray to optical ratio, where we don't know what the counterpart is, and we're also investigating those. I'll finish here. These are science goals of Eurozeta. I already described them in some degree of detail. Thank you.
Concerning the growth of supermassive black holes in the early universe, what is your present contribution? I mean, you can determine the masses of the black holes in some way?
Well, the most recent one, which kept me busy recently, we find supermassive black holes in dwarf galaxies, for instance. Dwarf galaxies. This is a very interesting topic. These are galaxies which do not interact with anything. This is where you can, well, not measure, but get some idea of what masses of the seed black holes were there. And like we have some couple of hundred dwarf galaxies where we know there is AGN activity, and for some of them, masses are being measured, and this is first thing which comes to my mind. And then, of course, we have, for tidal disruption events, we measure black holes there, and they're usually what we see in X-rays, they're usually lower mass, around 10 to the 8 solar masses black holes, and we have a program on Keck to measure masses of this with a high-resolution spectrometer, to measure masses of those, and that would add. So we use the way they do this, of course, from X-rays, we can only put lower limit from Eddington principle, from Eddington constraint. But then X-rays help us to pick up objects which deserve following studies. And then we can separate them into groups, types of galaxies, redshifts, etc. And then we can do dedicated optical observations and to measure masses. No, we don't get, well, speaking of redshift 6, we have this most distant object, which was known in the optical at the redshift 6.2, and we know its luminosity, and we construct volumetric luminosity. There is a couple of papers on this in monthly notices, and actually we derive lower limit on the mass of black hole, which is 2 times 10 to the 9. Redshift 0.6. So you can do whatever you want with this, but you'll have to build 2 billion solar masses black hole by redshift 6.
Well, this field is developing so fast that we are seeing, every one of us, and I appreciate the intervention of Felix, are looking to this object at different CN, different in GRP and in galactic nuclei acquisa. The great challenge is to understand how this different knowledge fit together in a global evolution. This will be one of the major issues which we will address during the meeting. For the moment, I thank already the presentation of Marat, and we go to, in this period, to a different topic, but related, which is Yerevan on the relativistic jet in tidal disruption events. Let's thank again.
Thank you. You need the microphone.
I should put this microphone on you, so you can put it in your pocket.
It works. Okay, good. Well, good morning, and I want to thank the organizer for the invitation. I'm very glad to be here for the first time in Armenia. And I would like to talk about relativistic jets in tidal disruption events. And basically, my point is to revise this old figure by Felix and to add next to it as a source of relativistic jets, tidal disruption events. And I think that in several places they are very significant. So an outline of my talk. First, I'll give some quick review of the classical pictures and some general remarks on TDEs in general, not necessarily ones that have relativistic jets. Then I'll speak about the first relativistic jet that we know from such events, Swift J1644. Then I'll talk on completely different phenomena, something which looks like a completely different phenomena, delayed radio flares in TDEs. These are radio emission that is appearing sometimes 1 or 2 years after the event. And I'll try to show
that they are directly related to these relativistic jets. And then a few words about the implications, in particular, the different types of tidal disruption events, why some have jets, why others don't have jets, implication to accretion physics, and to ultra-energy cosmic rays. So this is the classical picture which goes back to Martin Rissom 88. You have a star. The star falls in towards the black hole. It is disrupted, and then the matter from the star goes back, and it goes up, and some of it returns. And the return rate goes like t to the minus 5/3. And this was inferred that if the luminosity follows the return rate, then we should see objects that go up and then decay as t to the minus 5/3. And indeed, as you can see here on the bottom right, there are many by now optical tidal disruption events that you see the emission goes up and goes down. So it seems that the picture is fantastic and everything works, but there is a problem. The basic idea was that a small accretion disk forms, and this small accretion disk produces this emission. But if we have a small accretion disk, then we expect a total energy of about 10 to the 53 ergs, and a temperature of about 0.1 keV, and velocities of about 50,000 kilometers per second. What we see is something completely different. The peak luminosity is only 10 to the 44 ergs per second. The temperature is 50,000 degrees, at least order of magnitude lower than what is expected. The line width in the observations is about 5,000 kilometers per second and not 50,000. Again, an order of magnitude change. And the total energy which we see emitted is about 10 to the 51 ergs. So this is what I call the inverse energy crisis. We expect emission of 10 to the 53 ergs, and we see in most cases 10 to the 51 ergs. So there is some contradiction here. Not in all cases, but in many cases. And so what happens here? And you have to realize that just if you want to form a small accretion disk with a size of about 20 or 30 Rg, then just the energy that you have to dissipate in the flow to form the disk is 10 to the 52 ergs. Even this energy, which we call the circularization energy, is too large compared to the observation. So again, something is missing here. And what we propose is an alternative picture. And in this alternative picture, the emission that we see, the optical emission, is not coming from an accretion disk that forms, but it is coming from collisions within the stream. The stream, as I'll show you in a second, self-interact with itself, and in the self-interaction points that take place at few hundred to 1,000 Rg, then there are shocks. These shocks dissipate the energy, and the dissipated energy is the source of the optical TDEs. And this is a simulation done by Tower Yu, and you see here the disrupted matter going around the black hole and returning, and you see the returning stream interacting with the incoming stream, and this is exactly the region at a few hundred Rg where the interaction takes place, and this is where the luminosity, this is where the optical emission is coming from. So this is a completely different view of optical TDEs, and there is a debate now. I mean, this is our point of view. There is a debate in the community whether to accept it, but gradually people, more and more simulations are coming. This is, by the way, a fully relativistic simulation, and as far as I know, the most precise one, and but others are also supporting this picture. But now let me get to the real title of the talk, which is Jets at TDE. And the point is that not all TDEs are born the same. And the first event of this kind was Swift 1644. It has a very short rise time, about 200 seconds. It was detected by Swift. People thought at the beginning that this is a strange gamma ray burst, but it lasted for 10 to the 4 seconds, going up and down like crazy. Then the X-ray followed at T to the minus 5/3, not plus 5/3, there was a minus missing there. Sorry, T to the minus 5/3 decline. The observation of the host galaxies revealed that this is typically from the size of the central region of the galaxy. We expected the mass there, the black hole mass is about 10 to the 6 or solar masses, not much more than 10 to the 6 solar masses. The X-ray luminosity was the isotropic equivalent X-ray luminosity. If we assume that the emission is coming in all directions, then it was 10 to the 48 ergs, and 10 to the 48 is about 4 orders of magnitude larger than the Eddington luminosity of 10 to the 6 solar masses black hole. So this led the people immediately to conclude, well, there must be a jet, and there must be a relativistic jet, so there is a beaming, and the total energy is much smaller. But notice that for a jet to work here, and to be below the Eddington luminosity, the opening angle must be extremely small. It must be less than 0.01 radians, which is almost difficult to imagine. And I'll get back to this point. The total X-ray energy was about 10 to the 51 ergs. Total, I mean, integrated in time, because this phase lasted for about 10 to the 4 seconds. But this is, again, isotropic equivalence. But the strangest thing in this event was not the beginning. There are many puzzles about it, but the strangest thing in my mind was the very strange radio behavior. Because this event was discovered in radio, and as you can see here, the radio was increasing. And this increase in radio with time over the first half a year implied that the total energy of the radio emitting region, and now I'm talking about total energy, not beaming corrected, just everything that was there was 10 to the 51 ergs, much more than we saw in the X-ray. And also the strange behavior, what happens? Why is the energy increasing with time? Some suggestions, and this is, you see it again in radio, this is equipartition analysis, and so this equipartition analysis actually gives us the minimal possible energy, and you can see this clear increase here over about half a year of the implied total energy. So what is going on here? Some people suggested that this was a structure jet, that there was the cone was what we saw was the X-rays, and then there is a surrounding region which is slower, but also contains this extra energy. So this wider region is actually slower, but in fact it contains more energy. And now it's very popular to talk about structure jets following the observation of 1708-17, but this was even before that. So the idea was that there is a structure there, and as time goes on and things slow down, we see the radiation coming from the side. However, there are serious problems with this modeling. I don't have time to discuss them, but basically this model does not work. So there is still a puzzle what goes on here. So let me remind you of something which you all know from kindergarten, the issue of relativistic beaming. If you have a source which is moving relativistically towards you, the radiation is beamed. And this means that if there is an observer which is sitting not in the direction of the line of sight, at the beginning, when the motion is very fast, we will not see the source. Then if the object slows down, we'll begin to see it. And if it slows down even more, we'll see it even more. And what we suggest is that this is exactly what is happening here. What we are suggesting that 1644 was a jet that was viewed off axis. So at the beginning, we saw in the radio only a very small fraction of the jet because we were not in the main beam of the jet. Then as it was slowed down, we saw more. We saw even more, and then we saw the whole jet. This is when we saw the maximum. Sorry. We generalized the off-axis, the equipartition modeling to off-axis. The equations are too complicated, so I will not write them down. This was in a recent paper by Tatsuya Matsumoto and myself, and I will not even explain this complicated figure here, but the dramatic thing which tells us here, the fact that this line here crosses this line, told us just from this equipartition analysis that the jet axis, that the off-axis model is possible. And then once we realized that this model is possible, we went to a more detailed project of actually modeling this as off-axis afterglow. And this was done with Paz, who is here, and Tatsuya Matsumoto, who is not here. So the idea was actually, the machinery was almost there. We have to just tune it to this problem. So in an old work by Yoni Granot et al., they point out that if we have an off-axis observer, then we define this quantity A, which is 1 minus beta. Beta is the velocity of the jet. And then we have theta observer minus theta naught, the opening angle of the jet. So we have this quantity. And using this quantity, we can take these values, which are calculated from the standard modeling of the on-axis model, which we all know for many years. And by this scaling, putting A here and putting here nu over A, we can get the off-axis results. And there are some factors here that have to be taken into account depending on the viewing angle, and there is a normalization factor here, but this is just a little bit of arithmetics. But once we have these concepts, then we went and actually calculated the expected light curve from different, for an off-axis viewing angle, and you can see here the beautiful fit of the model to the observation. These are the radio observation in different frequencies as function of time. So you can see how good the observations are. As far as the X-rays, this model suggests that the X-rays are above it, so we don't have a contradiction with the X-rays, but the X-rays are coming from a different source, most likely still from the central engine. And here we can do this classical corner plot of the difference parameters that goes into the fit, and we can begin to discuss them and analyze them. What is most important here, that using this analysis, this is the first time that we can calculate and estimate the opening angle of the jet and the true energy. Because up to now, we had isotropic equivalent energy, and we had to guess, at least in the context of these events, what is the opening angle, and there was no clue on this factor. So we know we can estimate the isotropic equivalent kinetic energy, but not the opening angle. with this opening angle that we calculate here, and we also have the viewing angle, we can calculate the true kinetic energy. And not surprisingly, it agrees with what we got early from the radio estimates, which says it is a few times 10 to the 51 ergs in this event. Now let me jump to a completely different issue. This analysis also tells us what is the radius of this where the emission takes place, and it is about 10 to the 17 centimeters. And also, what is the magnetic field at this region? And this product, B times R, in units of Gauss term centimeters, is exactly the critical thing which you have to know to estimate whether you can accelerate or not particles to a given energy. And this is the Hillas figure here. And this allows us to put TDEs as a new point on the Hillas diagram. This TDEs, jets from TDEs are potential sources of ultra-energy cosmic rays. We actually knew this already in 2014. We have a paper with Glenis Ferrar on that, which we never bothered to go through the full referring report, so it's in the archive. But I'm very proud of this kind of papers because it's just on the archive is more than 60 citations by now, which means that we don't need the Nature and Science to make propaganda for you. But now we are even more, but we had some doubts. And the doubts were about how often we have these jets. Do we have enough jets of this kind to produce the whole population of ultra-energy cosmic rays? It is clear that these are a viable candidate, but do we have enough energy to produce all of them? And the next part of the talk will show you, yes, we have enough. So now let me jump to to a different topic, which was a discovery by my colleague in Jerusalem, Asaf Choresh. And what he discovered is late radio flares from tidal disruption event. So you have a tidal disruption event, the optical emission went up, and then it went down, and you almost forgot about it. And most people forget about it, apart from some theoreticians who still keep trying to figure out what happens there. But then Asaf was persistently looking at radio at these events, even few years after the event. And this is, from this paper, are delayed radio flares common. So this is the event here. And you see here upper limits, and then this huge jump. In this case, it was only 150 days after the event. But this event here is much more dramatic. Nothing, just upper limits. And then 3 years after the event, boom. And the things goes up as t to the 5. Now there is no typo here. It's not t to the minus 5. It's t to the plus 5. It goes up like crazy. Where t is measured from 0 here, not this. It's just skyrocketing. So this is this is 2018 HYZ, and this is a preliminary. We are still doing the final things on that. This is from paper with Itai, who is a PhD student, Asaf, that I just mentioned, Paz, who is here, myself, and a few others. So we see here this dramatic rise that I mentioned before. This is, again, this dramatic rise compared to other events. What is happening here? And what is happening here is that we again have an off-axis event, but now the viewing angle is very far. Before, the viewing angle was very near, so it was off-axis. In 1644, we could see the event even at right from the beginning, because it was just slightly off-axis. But here we at a large angle, something like 50 degrees away. So at the beginning, we don't see anything. But there was a very powerful jet. And we wait with this powerful jet, and then after 3 years, we begin to see it. And then, as the jet propagates, first of all, it accumulates more matter. So this by itself should give rise like T cubed. But this is not good enough. But the increased effect that you see larger region of the jet gives you this other extra power of T squared. And altogether, we get the T to the 5. So this is, again, a preliminary summary of this event. We see here the very nice fit of the different bands of the light curve. We have a clear prediction of a peak here in the radio, which will be very easy to measure in about a year from now. So there is a clear prediction here about that should be tested, and then there should be a decline once we see the whole jet. And then we have a preliminary this analysis of the different parameters. And the remarkable parameter here that this was a very powerful jet. That the totally involved energy was again more than 10 to the 53, approaching almost 10 to the 50, more than 10 to the 52, approaching almost 10 to the 53 ergs. So this is a very powerful jet. And this suggests that the earlier statistics that said, oh, we had only 1 or 2 direct candidates in which we saw jets in GRBs, therefore there are only very few events like this, may be misleading. These events may be more common, much more significantly more common than what we thought. Now, there is, of course, a question, why some events have these jets and why other events do not have these jets? Because these delayed radio flares are not that common. They're about half a dozen or so by now. We don't see them in every TDE. And now this is a speculation. And the speculation is that on the y-axis, we have here the angular momentum of the incoming star, which corresponds to the distance of the incoming star from the black hole to the pericenter. So if the angular momentum is large, the pericenter is far. If it's too far, we will have a phenomena which is called the partial disruption. Just fraction of the star will be disrupted. Most of the star will remain intact. If it's sufficiently close, we get what we call regular common full tidal disruption, and this gives this standard typical optical TDE. But if it is very close, then we'll have a circularized TDE, and this in circularized TDE, accretion disk does form, and these are the events that cause jets. If it is even more nearer, then if it passes something like 4 or 5 RG from the black hole, then there is a different story. We call it extreme TDE, but this is subject for another talk. So this is again a summary of these different types of disruption. And what we speculate is that these events here, which come at a distance of about 10 RG from the black hole, are these events with strong upsidal deflection, and this strong upsidal deflection produces accretion disk, and this produces these extreme events which are very efficient and have jets. So to summarize, TDE comes in different varieties. Some of them are less vigorous, less active, and some of them are extremely active. Some produce very powerful jets, 10 to the 52 or more ergs in these jets, and they are relativistic because everything that we saw here is based on the fact that the jets were relativistic and this beaming effect. There are many late radio flares, or there are the late radio flares are possibly or most likely jet viewed off axis, as we have seen here. The large total energy implies that some TDEs are very efficient in converting the disrupted stellar mass to energy. Most of them don't, but these are. And these TDEs can be the sources of ultra-energy cosmic rays. We still have to work out exactly the statistics, but with this amount of energy and with the rate implied by the late radio flares, we can possibly produce the whole ultra-energy cosmic rays fluxes. Thank you.
Thank you very much, Sri. Yes.
I have three rapid questions. One, can you generalize this mechanism of, because delay radio emission is observed in microquasars, in commemorate burst, in AGS. This is the first question. And second, does it fit the interpretation of adiabatic expansion of the jet that is seen in changes, progressive changes in the big frequency of the radiation?
So the second question is, the answer to both questions is yes. As for the adiabatic expansion and the change in the frequency, this is exactly the calculation that I was presenting, that Paz was doing, and it was doing it. You have the adiabatic expanding gas, and this gas interacts with the surrounding gas. This changes, as it slows down, it changes the typical frequencies, but we can calculate the whole thing this is the details that go into this calculation. And as far as the delayed radio emission, yes, it is possible that similar phenomena happens also in other events, and let's discuss it in some of the breaks, whether because I'm not familiar with the details of this event. But this is a classical situation in which a jet goes in this direction, you don't know about it, and then suddenly in the radio, when things slow down, you say, there was a jet here, and now suddenly I see it. This is exactly the picture that we have here.
See, there was this plot with the impact parameter versus mass of black hole, where you classified the events.
Yes.
My question is there understanding how X-ray emission maps onto this plot? Where which events, which combination of parameters would lead to more X-ray emission or to less X-ray emission?
There are two types of X-ray emission. From the regular GRBs, which are the majority, you don't see early X-ray emission. TDEs. Sorry, TDEs, yes. From the majority of these TDEs, you don't see X-ray emission initially because there is no disk. But after some time, the disk forms, and then you will see X-rays. So you will see the X-ray will appear later. This has been seen in some cases. The most exciting events for X-rays are these ones. Because in this one, disk forms very quickly, and here you have accretion disk, and the accretion disk typically is emitting an X-ray.
Yes, I think every one of us has so many questions and discussion to go on, and I appreciate very much this very general introduction by Sri. I would like to stress, however, that we are in this meeting living in a very special moment in which data of incredible new value are being presented. And in particular, in the And I thank first of all for this very interesting talk, and I move on a different set of talks, starting with the presentation of Sofita, then going on the Capitanio source, and then a contribution exceptional made at a distance by Enrico Costa. I would like to highlight that these results are absolutely new, and they point although from our point of view of conceptual understanding, to new physics, namely on the possibility that in some pulsar seen with interferometry, X-ray interferometry, with a new telescope, there is evidence not just from the pulsar emission, but from the remnant, a new X-ray polarimeter measure that show in the remnant around the pulsar, and I think they have two beautiful examples, the Crab and the Villa, which we will see, there is action in the remnant. To me, this is the most strong possibility that there are black holes present in the remnants. And these 2-3 lectures is a new technological approach looking for polarimetry. It's new. Therefore, the interpretation is still to be done to all of us. We have some idea, but I invite everybody not to think now about only the concepts, but about the data. The fact that there is something new in a pulsar, in the remnant of the pulsar, showing polarimetry. This is the new idea, new fact, observational fact. And it's spectacular that this contribution was presented, one view careful, was presented by this new X-ray telescope invented, like the one of Sachs, again by Enrico Costa. Therefore, we will have the great honor to have Enrico Costa to present something at the end. But again, these two contributions, I invite you, don't just look. It's a new substance. Okay? Please.
Thanks, Remo, for the nice introduction, and I thank the organizer for inviting me to speak about IXPE. IXPE is the Imaging X-ray Polarimetry Explorer, and is basically how. Thank you. Thank you.
Okay, please.
Yeah, it's probably something off in the mental.
Okay. Okay. It works. Thanks. So why X-ray polarimetry in X-rays? Because actually polarization process themselves provide polarized radiations, but also if the radiation is emitted thermically by scattering in disk blobs and columns, it can assume a certain degree of polarization. And moreover, it's possible to have information on vacuum polarization birefringence through extreme magnetic field by X-ray polarization. In order to measure polarization, we need to measure a modulation curve. From the modulated term, we derive the polarization. From the position of the peaks, we derive the angle of polarization. This is equivalent to actually use Stokes parameters. The first important thing to understand is that polarimetry is a matter of photons. We need a lot of photons to arrive to measure polarization of the order of 1%, more than 700,000 counts. This has to be compared with 100 counts needed for measuring a spectral slope and 10 counts to make a source detection. ICSPE is a NASA ASI mission, which the PI is hosted at the Marshall Space Flight Center, and ASI funds the detector system that has been completely devised, assembled, and calibrated in Italy by INAF, NFN, and the industrial partner. The Mission Operations Center is at ASP. There are other institutions involved on science theory. This is the ICSPE observatory, in which we have a free mirror unit that actually are placed at 4 meters with respect to the detector unit that are on the bottom. The detector unit hosts the polarization sensitive detector. And this is after deployment of the boom, the ICSPE experiment. That was actually devised to be launched on a Pegasus launcher with a very small resources in terms of volume and weight. This is actually the launch that has been done in December 9, 2021. You can see here the returning of the Falcon 9 first stage on ground. This is the moment in which the satellite has been developed, has been expelled by the second stage. This is the mirror module assembly properties. It's a very thin mirror, the thinner mirror fabricated by Marshall Space Flight Center that has a 4-meter focal length and about 170 centimeters square for each mirror. There are 3 mirror units. The angular resolution is about 18 arc second, 19 arc second for mirror number 1 and 25 arc second for mirror number 2 and number 3. And during flight, convolved with the detector, we have an angular resolution of 30 arc second for all the 3 views. To measure polarization, we actually use the photoelectric effect in gas, for which the emission direction of a photoelectron is directed preferentially along the direction of the incoming beam of the photon. In order to, we actually proposed this detector for a number of tentatives, while back in 2017 we were selected by NASA as a NASA's MEX mission flown in 2021. In order to measure polarization, we had to make the image of a track produced by a photon in a gas, and we are able to actually determine the conversion point that is by the image that is related to imaging, the emission direction that is related to polarization. We measure the charge content in each pixel that is related to energy, and the signal output that is related to time. So with ICSPE, with a single instrument, we can do resolved X-ray polarimetry resolved in energy, space, and time. The calibration was performed in our institute in IPS. It took for each detector 40 days, 7 days a week, 24 hours a day, to carefully know the response of the instrument to polarized and unpolarized sources. We have on board a filter calibration wheel that we devised that hosts on board either polarized sources and unpolarized sources. These are the results of the calibration source on board with the image on the top and the modulation curve on the bottom with the two polarized sources on the left and the unpolarized source on the right. These are the detector properties. The spatial resolution is better than 120 micron, that is about 6.4 arc second at 2 kV. That means that we are dominated by the optics in terms of angular resolution, not by the detector. The energy resolution is 1 kV at 6.4 kV, and the useful range for polarimetry is between 2 and 8 kV. The modulation factor increases with energy as expected, and the precision with which we can measure the polarization angle is better than 1 degree at all the energies. The response of the detector is this one, that is about only 80 centimeter at about 2 kV, 8 centimeters square, about 2 kV when we convolve the optics with the quantum efficiency of the detector. And we have to understand that we do dithering. We don't do observation steered, but we actually move the satellite in order to actually sample a portion of the field of view. And this is done because so we can average out the systematic effect and facilitate the on-ground calibration. We explored a different astrophysical target with ICPE already. Active galactic nuclei, microquasar, radio pulsar and pulsar with nebulae, supernova remnants, magnetars, accreting neutron stars. For each of them, we were able to measure polarization. And for the first year, this is the list of first year target of IXP, mostly on the galactic plane and some outside the galactic plane, for example, for blazars. And we observed up to now 48 sources, and some of them have been revisited for all the classes. And if we consider the quick look analysis with the phase, time, and average measurement of polarization, so taken all together, we get 19 detection at more than 6 sigma of polarization on 48 sources. However, if we do in the detail phase, time, and angle resolved polarimetry, the number of detection increases a lot, and about, let's say, 2/3 shows a polarization of a certain level. So, regarding astrophysics, we clearly, one very important measurement that we did is doing angular resolved polarimetry of pulsar with nebulae. And for example, we know that the Crab pulsar with nebula is very complex with jets, knots, arcs, torus. And indeed, when we measure polarization, we measure the same the first time was in 2022, where we measured the polarization consistent with the measurement done back in the 70s by OSO 8. In 2023, we remeasured the polarization of the entire nebula, and is about the same, but with a much more tight error bar, because of the improvement of the pipeline. So we are very happy of that. If we consider the polarization with the comparison of the polarization with respect to OSO 8, we see that basically that the polarization, the degree of polarization is the same, but the polarization angle is shifted about 10 degrees. There is also a change in the polarization angle in our data between the low energy 2 to 4 kV and high energy 4 to 8 kV. And this has also been seen for the off-pulse so the nebular part, not only the pulsar plus the nebula. If we see here on the top right, we see the polarization degree as a function of the angle and the function of the position. We see there are bright polarized data up to 45% on the top on north, east, and southwest. And if we map the magnetic field with the IXP, we see that the magnetic field map the toroidal structure of the nebula that has been seen by Chandra. The level of high degree of polarization suggests that the turbulence is not as strong as predicted in this system. For the pulsar, we were able to measure polarization at more than 3 sigma only in the first pulse, in the core of the first pulse. However, the upper limit measured in the different part of the pulse says that the swing of the X-ray pulse should be faster than the one that has been seen in the optical light. The Vera pulsar with nebula showed an even larger polarization. The integrated polarization on all the nebula is 45%, and while in the crab is 20%, and in some region is as large as 60%, that is very close to the synchrotron limit. Also here, the large polarization that has been measured is in connection with the low turbulence in the magnetic field. Supernova remnants, we measured 3 supernova remnants, polarization from 3 supernova remnants, Cassay, Tycho, and SN106, in order to measure the polarization of the supernova remnants. For Cassay, we measured polarization between 4 and 6 keV, where the lines are not present, the thermal lines are not present, so we concentrate only on thermal emission. And we actually rotate each photons according to the azimuth with respect to the center in order to collapse a 2D problem in 1D problem and get therefore statistics. And for this, we actually end up with a polarization that is preferentially tangential with respect to the remnant. That means the magnetic field is radial. For Cassay, the magnetic field is radial as in the radio, while the polarization that has been measured for non-thermal emission is about 2–5%. This means that actually there is a realignment very close to the shock of the magnetic field toward a radial direction. The same we measured for Tycho, in which actually also here the polarization angle is radial, and the polarization degree is larger than the one measured in Cassay, maybe saying that it's a less turbulent magnetic field, or the turbulence scale is larger. We also measured SN106, we are writing the paper, and we have consistent results also with supernova 106, with increasing polarization from Cassay, Tycho, and SN106. For magnetars that are neutron stars with the magnetic field up to 10 to the 15 Gauss, we actually measured polarization from for U01, 42 plus 61, and this is very curious in a sense, because at low energy the polarization is small, then it becomes 0 between 4 and 5 keV, and then it rotates 90 degrees at higher energy. And this is modeled by saying that the radiation at higher energy is due to the resonant Compton scattering and produces the power law that is polarized in X mode, so perpendicular to the magnetic field, while the radiation at low energy, the thermal emission, is due to a condensed surface that emit O mode at a low value of the polarization degree. And for another magnetars, we measured a completely different behavior. The polarization angle stays constant along the energy, and we end up with a very large polarization up to 35% in the averaged, but it can become, when energy is resolved at a value that is larger, that is about 80%. Regarding accreting neutron star, we had a surprise because we were expecting polarization between 60 and 80%, and we end up with a polarization, for example, for Hercule X1 of about 8%. And this is very challenging for the models, as we know. And however, by looking to the swing of the polarization angle with respect to the phase, it was possible for the first time to measure the inclination, the spin of the neutron star with respect to the sky, and the angle between the magnetic axis and the rotation axis. With SEN X-ray, we measure an even smaller polarization, about 5–6%. And again, here we see that the polarization degree is anticorrelated with the pulse with the source flux as a function of phase. And a clear interpretation should go in considering all the aspects in terms of reflection and scattering of the primary photons by the surrounding material of the binary pulsar. We also measure the polarization from LS-V44 in supercritical subcritical pressure rate, and we see that phase resolved polarization degree and angle are very different for the two states. Regarding accreting stellar black hole, we want to measure polarization of accreting stellar black hole, either in hard state to understand the corona, and in soft state to understand the spin of the black hole. We measure the polarization of 4% integrated on all the energy. That is very large with respect to what is expected for the low inclination orbital system of Sinus X1, but we measure also a polarization angle that is parallel to the jet of the black hole. And if we consider what is the polarization angle with respect to the jet of the black hole in terms of geometry of the corona, if it's a sandwich or is a lamppost, so on top of the black hole, we see that the lamppost corona is excluded, while the most favorite one is sandwich corona. And the fact that the polarization degree is of the order of 4% is taken into, people think that this is maybe due to the fact that the disk realign with respect to the orbital plane. We measure polarization also from extragalactic sources. With blazars, we can measure polarization due to the energy band of synchrotron-dominated blazars and inverse Compton-dominated blazars. And for asynchrotron-peaked inverse Compton-dominated blazars, these are measured for Markarian 501 and Markarian 421, and indeed they are remarkably polarized. The polarization at X-rays is larger than factor 2–3 larger for Markarian 501, is larger than 2–3 with respect to the polarization in optical and in radio band. The polarization angle is aligned with the jet or Markarian 501. If we duly complete the different expectation in terms of multivariate polarization, variability, and polarization angle, there is a strong preference for an acceleration due to the shock in an energy stratified environment with turbulence that becomes larger and larger as far as the particles goes out from the shock. For Markarian 421, we measure the polarization that is about 7 times the one measured in optical and in radio, and this is also explored in the context of shock acceleration in a stratified energy, in energy stratified environment, and but this time the polarization angle doesn't coincide with the polarization with the jet direction. For radio quiet AGN, we actually can have an indication on the polarization, on the geometry of the corona. And for example, we measure polarization of MCG 52316 with 3.2% of upper limit, and a similar result for EC4329A, while for MGC 4151, we measure indeed the polarization, a significant polarization of 4.9 plus minus 1.1% that is aligned with the radio jet. And this alignment of with the radio jet, with the respect, with the similarity of Sinus-61, makes a preference that the corona is preferentially sandwiched around the accretion disk. We also explored polarization of Compton-thick AGN, in which the AGN is seen almost a John and is covered by a thick molecular torus. And we measured the polarization this time that is for the cold reflection, that means the reflection by the torus, of about 28% plus minus 7%. This time the polarization is perpendicular to the axis of the torus because it's expected the scattering has this kind of geometry, so the polarization is perpendicular to the torus, and this is actually is being used in order to extract the information on the upper angular aperture of the torus itself, knowing what is the inclination of the torus. That is about between 45 and 55 degrees. So I think I finish here for the presentation, saying that ICPE has been approved for an extension until September 2025. Is it already possible to put at EASARC some request for geo observation, and the deadline for geo for request observing program will be 18 October 2023. So the data that are already public, they will be competitively assigned to by a general observing program, and so basically one can actually decide, the community can decide which sources for how much time is possible to observe with IXP, while until now the observing plan is decided by the team. From starting from February 2024, the program will be decided by the community. So this is my last slide.
Thank you very much, Paolo, for this extremely extensive presentation. Very successful, very new, with an instrument very light, you have seen, guided marvelously by a small team. We will hear the presentation in a moment by Enrico. And I think I I would like to focus your attention, but of course, on two, and I will let people ask, but let me direct the key point. The key point is that polarization is seen all over, article, antinuclear, whatever. You see, therefore, more information. But to me, the most exciting point is that in the case of the crab, you don't see the polarimeter emission from the crab itself, but you see from the supernova. This, I think, is conceptually completely new. Therefore, this instrument will be enormously important for antinuclear, for all this, but it's unique in showing that there is no correlation in the pulsar in the crab, and that the polarization comes not from the pulsar itself, but from the supernova. This is conceptually revolutionary, and it could imply, I think we are really dreaming with Yerevan, that there are many more black holes in our galaxy than we expected. And associated with the crab, there could be very well a black hole. But I would like also to remember, and I think the next talk will cover this, that not only this happens with the crab, but also in the Vela.
Vela, I just very, yes, also. But, no, I just showed some results on Vela.
Now,
yes.
You should stress more that the Vela results were obtained by the Chinese.
Yes, Chinese Fei Shi of Guangxi University, that is also enough associate.
Yes.
And
what is your name?
Fei Shi. Fei Shi.
Okay. We hope to have her here because the fantastic result is that this is the key point. The fantastic result is obtained both in the crab and in the Vela. And this result was really obtained by this very young student in Italy from China and published in Nature in the first part. This is the key point. They are remnants with inside, they have very strong polarimetry X-ray emission, and they could be related to black holes. If that is the case, pulsar and black holes are part of the same phenomenon. But this will be the topic for the next Marcel-Grossman meeting in Beijing, where we will see all this contribution and the physics associated. But this is the message. Okay, let's go to they were certainly some question by Felix.
Yes,
We
very quick.
last night.
Yes. In Cygnus X1 and jet sources like Cygnus A, you said the polarization along the jets is always along the jets, but in the lobes where the shocks take place, is there an observable change in the polarization?
In the shock, you mean close to the black hole?
No, the shock, for instance, Cygnus A.
No, we don't have the angular resolution to resolve the jet like in
the lobes.
Yeah, in the lobes. No, we don't have the angular resolution for doing this. Okay. We can do only measurement integrated. For Sene, we tried, but the jet is so faint that we actually have only coarse upper limit. But for Sene, we were detecting the jet, but with very low counts. Since we need very large number of counts to do polarimetry, we end up with an upper limit.
Okay, thank you.
again, before changing, the key point is you expect you see polarimetry, everything where you expect, but you see X-ray polarimetry very distinct in place, which we did not a priori expect to have namely not in the pulsar, but in the associated supernova. This is absolutely crucial. But we will discuss in the next time. Okay. And we go now to Capitano, and then later we will hear the person who conceived this instrument, which will transmit directly from his institute in Rome, which is Enrico Costa.
Yes.
But it's really exceptional, this result. I hope you will realize and follow in the months to come this new physics. There is the possibility that there are many more black holes inside our galaxy than we expected before. This is the crucial point.
If I put it in the pocket? Yes, if work, I don't know if it works with my computer. Okay, perfect. This is the last. I don't know why, but this is the last slide. Okay, thank you. I don't know. I'm not able to start the presentation, I'm sorry. Okay, I can start. Good morning, everybody. After the nice introduction of Paolo about the IXPE results, I have the occasion, thanks to the organizer that invited me to have this talk, to go in details on when new science can, when the new science can give you unexpected results. And this is what happened with the low mass X-ray binaries, for example. Just a brief introduction to the object. A binary system where there is a compact object that creates matter from low mass X-ray binaries, from a low mass companion star. All these objects are old objects, so they are concentrated in the galactic center or in the globular clusters. The compact object can be a neutron star weakly magnetized or a black hole. The majority of black hole systems are transient, while neutron star systems are can be either transient or persistent. Anyway, they are all very variable sources with a very small orbital periods. This means that are very compact system. They are classified historically with a color diagram for neutron stars and hardness intensity diagram for black holes. And this is why we search for that this is something that is repeatable in the during the outbursts, especially, or also for persistent source. In fact, for example, neutron stars draw the same track on the color diagram for every outburst, or even when the sources are persistent, they go up and down in the same color diagram. There are two accretion regimes. The first one, the atoll sources, and the zeta one, and the second one is called the zeta sources because of the track they draw in the color diagram for neutron stars, and they are different accretion regimes. But they are not two kinds of different kinds of objects, because there are 2 or 3 cases that can show both accretion regimes. In case of black hole binaries, each outburst, with some exceptions, can go through all the spectral states, and starting from quiescence, go to hard state, come back, there is a major transition to soft state, and then come back in quiescence. But the luminosity, it's different for every outburst. So this Q track in the hardness intensity diagram can be at different luminosity for every outburst. The spectra are different. There are 2 main spectra, hard state and soft state. They are both a combination of a direct emission of accretion disk and reprocessing radiation due to inverse Compton scattering via a corona of hot corona of electron, a plasma of hot electron corona. For neutron stars, we have a temperature of the plasma about 3 keV, and in ice of the state. Sorry. In low hard state, the neutron star has about a temperature of about 20 keV, and the temperature of the corona, and there is sometimes sign or reflection component, and there are for neutron star system in low hard state, there is the signature of the presence of a solid surface of the neutron star with the type 1 X-ray burst that should be very, highly polarized, but very difficult to detect with IXPE because they are very short. In this case, we are in the same situation of black holes, but in black holes, the temperature of the corona is higher. And so the spectrum is harder, and until several hundred keV. In this case, either for black hole and for neutron stars, IXPE can study the geometry of the corona, as Paolo showed you with the Genius X1. In ice of the state, the situation is different from neutron stars and black holes because of the solid surface of the neutron star. The disk extends until the surface of the neutron stars, so the spectrum is more soft, and there is a reflection component due to the reflection of the scattered photons in the disk that is more prominent and more common to be observed. The presence of the neutron star surface can make the difference, because probably the corona of electrons is no more a sandwich corona, but could be the transition layer itself between the disk and the neutron star surface. So IXPE and the polarization measurements could make the difference to understand the geometry of the corona and the origin of the Comptonization emission. And in ice of the state for black hole, the situation is different, because in the energy range of IXPE, we should see almost the disk emission. and the corona emission is higher, and it's totally different because it's thought to be due to non-thermal electrons, plasma of electrons, and in fact in the spectrum the spectrum has a power law like spectrum until 700 kV without cutoff. IXP observed these low mass X-ray binaries. We can show also some results from CubeSat mission polar light that observed SCOX-1 and observed 2 zeta sources, 2 atoll sources, and 1 black hole binaries. And before the IXPE launch, there was the people from working group realized that there was not any theoretical simulation of the emission that predict the emission of polarization in function of inclination or energy for neutron star black hole binary, neutron star X-ray binaries, while there are several studies for black hole binaries. So in 2022, Niarini et al., that is a young student in Roma, Third University of Rome, publishes this paper where adapting a model created for AGN to neutron star systems can studied with different geometry of the corona in function of energy and inclination angle. And but all the are the XP data in agreement with previous theoretical works? In this case, the answer is probably not, because we can start with zeta source, what we obtained. In SCOX-1, just in 2028, was launched in 2028, but the first results arrived in 2021. And we see that, sorry, this is Genesis 1, X2. And this is one of the first sources observed by XPE. And we know a lot about Cygnus X2, but these are the spectrum obtained by a broad simultaneous observation with other observatories with IXPE in order to obtain a broad spectrum and to fix the spectral parameters of the source, because IXPE has a small energy range, so it's not easy to have a very detailed spectrum. And what we obtained is a standard spectra of this kind of sources, but we obtained from IXPE data that the source, is from the color diagram, the source is in the normal branch. And this is important for the results that arrived after. And the polarimetric analysis, we see a very a polarization of about 2% in 28 kV that increase, there is a clear increasing in energy. And moreover, we have that the polarization angle is aligned with the radio jet, as in Cygnus X1 results. And we know this because we were lucky, because neutron star systems are not often observed in radio band, but there was a relativistic emission in one of the archive data, radio data, that are aligned with the polarization angle. And moreover, applying spectropolarimetric analysis, we can say that most of the emission is due to the Comptonization component. SCOX-1, now it's the turn of SCOX-1, that observed by polar light. In the polar light CubeSat has not the sensitivity to make detailed studies to this kind of object, was able to observe only SCOX-1 because it's the brightest source in the sky, and observed he observed a lot of time the source in different moments and obtained only 4% in one specific observation when the source is probably in the normal or Frey branch, and obtained a value of 4% that is out of any rule out any prediction. Moreover, this was one of the most important results we obtained only with IXPE, this nice work from Massimo Cocchi that has been accepted for publication, I think, 10 days ago. And the source was a serendipity observation because it's a transient source. It was not in the plan of IXPE. And we observed this source 2 times, and the first observation was in a horizontal branch of the zeta. It's a zeta source, or can show the source can show both behavior, zeta and adult source, but we catch it in the zeta regime. And the first observation was in the normal branch and horizontal branch, and in the second observation in the normal branch. And what we can see is that in the first observation we have a very high polarization degree, about 4.5%, and in the second observation we have a polarization degree that is about 0, compatible with 0, and with a very teeny detection, not at 2 sigma level. And even in this case, we have for the first observation that the polarization seems to come directly from the Comptonized component. And then and moreover, it's important that we have in preparation another paper on GX5-1 that confirm this prediction that the polarization depends on the branch of the zeta source. For adult source, the situation is different, totally different, and we have 2 observations, and this another one is still in preparation. And this is the first observation of low mass X-ray binary made by IXPE, and we have also a spectrum that is consistent with the standard spectrum with this kind of sources. And what we obtained is unfortunately a polarization that is compatible with 0, and this was the first observation at all, so we were very upset with these results at the beginning. And we try to fit our results that were only upper limit of with the polarization less than 1.3% with the theoretical simulation, and the only geometry compatible is spherical geometry. And then we observed an GX9+9 that, on the contrary, it has a little polarization of about 1.5%. And this polarization increases with the energy and comes, okay, there is also a reflection component in this source. So we made a spectropolarimetric analysis to try to disentangle if the polarization comes from disk, from comptonization, or from reflection. What we obtained is that we have no statistics to decide if the polarization comes from reflection or from comptonization, but probably from the sum of the 2 components. In fact, reflection could, even if it's small, could be highly polarized in the Thomson regime. This is the resumming what we found that fitted with the theoretical works, and it's clear that we are observing something different on what we expected to see. Sometimes the polarization is higher, sometimes the polarization is low, and so it is not. it is also it seems not there is a dependence on the inclination. SCOIX1 is an inclined source, not very favored to have a very bright, a big percentage of polarized emission. And it's one of the most brightest source in polarization. And just we can pass to black hole systems. Unfortunately, black hole systems are all transient, so it's not easy to observe. And we have only one case that we were able to observe, but it's for use 1730. That is a Luma 6 ray binaries. That is not a standard example, so it's difficult to have an answer on what we are observing. First of all, I will just give you some details on the theoretical works developed before the IXPE launch, and these are the most recent paper. And as we can see, we expect to see in the polarization in function of the energy some signs of the spin of the black holes. These are two extreme examples of a very inclined source, spin at 0, spin almost 1. In this case, the features are outside the range of IXPE, but for less extreme spins, we will have this sign in the polarization degree and the rotation of the polarization angle inside the range of IXPE. And what we observe for U1613 that has been observed in soft state, what we observe is a very large polarization degree, not explainable with the theoretical works, and no rotation of the angle, and no features that can be observed inside the spectrum, but anyway, the errors are large, so we don't expect to see the features in the polarization degree, but we expected to see the rotation angle. The source was observed 3 times, one in pure isoft state, the other 2 in steep power low state with a very important contribution to the comptonization part of the spectrum. So no rotation of polarization were detected. The polarization detected was very high. No variation with polarization with the source state. The spectra are very different, but the polarization is almost the same. In the first observation, we have sign of absorption feature due to the wind, and there is no wind in the other 2 observations. So there is a paper published by a concurrent group that claims that this polarization arrived from the wind. This is not true because we see the same level of polarization in the other 2 observations, and there is no wind in this case. And what we have to say is that this source is a peculiar source. In fact, the hardness intensity diagram is not followed in this case. This source lacks of bright hard state, and probably the only explanation that could say that there is not a rotation of the angle is that it's a low spin source, and this is also could be also a reason that the strange behavior of this source. I let here my conclusion. We observed a higher polarization than expected. We observed that when we know the direction of the jet, the polarization angle is directed in the same direction of the jets. All the results says that the polarization coming almost from in the case of neutron star system, is coming from comptonization component, and we didn't observe signature of black hole spin of the black hole in black hole systems. So, thank you.
Thank you very much. I think there will be a huge amount of work to follow. We are, as you recall, this is a new era of a new instrument and a new observation of X-ray polarization. We are revisiting all the previous system, including, let's not forget that the first object observed as a binary, proposed by Shklovsky, was COX-1. And Ricardo published the fantastic paper about the discovery of the first X-ray emission coming from outside the solar system. We are seeing marvelous results, and we are revisiting systems like SCOX-1 that have been discussed for decades, but now with absolutely new data, refined. Every visit of this object, in my opinion, I speak to delay, will have to be reconsidered at the next Grossman meeting to see, while this publication of this polarimetry is going on in these days in all the advanced magazines, we will have 1 year to revisit SCOX-1, to revisit Cygnus X1, because to me, to have a magnetic field polarized in Cygnus X1 was a dream which I never had when I proposed Cygnus X1 as a black hole. But now we have the polarization of the magnetic field. It's incredible to jump. In Beijing next year, we will have to have parallel session revisiting all the classical systems from SCOX-1, Cygnus X1, and so forth. Okay? But now, before we listen, well, we will have informal discussion, but let me stress the key point. To me, the key discovery of this XPE is not only to find polarization everywhere that was expected with enormous more attention and detail. This is a great result. But to me, as a black hole physicist, and I am sure we will come back to this with Felix later on, the key point is that you find polarization where we did not expect, namely in the remnant of the Vela pulsar, the fantastic result of Feixier, and in the crime. We don't find polarization from the pulsar, we find polarization from the remnant. This is enormous. This means, of course, you find polarization wherever you had to find, but you did not expect polarization from the remnant of the supernova. And this is the great result of Feixier, and a great result for the Vela, and a great result from the crab. It's totally new. I hope we get the point. Okay.
Yes.
Please.
The systems, the parameters of the compact object that you are inferring are compatible with previous inferences, for example, from QPO models?
For SCOX.
You mean black holes or neutron stars? we don't know anything about this source. This source is not well understood. It is not sure if it is a black hole or neutron star, but from the spectral point of view, it is a black hole. It's a very peculiar source. It is, for you, 1730 is not the best case to study for the first time, but these objects are transient, so we have only this occasion to observe this source. So we are waiting for GX 339-4, that is a standard black hole to have.
But Olga, if I may add to your request, of course, one thing is the definition of the mass, the parameter of the binary and so forth, but there is something much more revolutionary. The fact that single X1 initially of 3 solar mass is now an object of 10 solar masses. And from these results, you have a magnetic field with polarization. And you observe this. This is enormous. Enormous. It's not only in SCO-X1, of course, with respect to the old work of Ricardo, you can improve the mass determination. Of course, that is very, very important. But there is all the new physics of SCO-X1 coming up. I think we should really program in this year to come a revisit of all the historical sources and what we are learning from this. Let's go, if we can have the voice of the man who did this miracle, which is Enrico Costa. I want to, for the people who don't know, of course, we have been brought up in knowing the Beppo-Sachs and the revolution of the X-ray afterglow, but we forget at times that Enrico was in the team of Beppo-Sachs and was inspiring of the Beppo-Sachs. Now, at this, we are both young, but not too young, but we live that adventure together with Enrico. But I ask him to say a few words now on this new experience that we are living, me as observing and him as inventing this fantastic new satellite. Very elegant, like already Beppo-Sachs, very elegant, very simple, but crucial. I mean, look at the geometry of this object looking around very light and finding, thanks to him and his team, the polarimeter data. Sei pronto? Puoi dire qualche cosa, Enrico? Ti vedo. Eccoti. Go on. It is Enrico Costa, for you to see, because he is the man.
Of course, not the American group, it's not a single person, but certainly he has been the person who had the idea to push and to accomplish the mission. Of course, there was an international collaboration, NASA, Italian Space Agency, many.
But I want to hear a few words from Enrico, because he was the inspirer of this mission. Andiamo? We lost the connection.
Yes, there is connection problem.
It is connected.
Let's wait a few minutes.
Able to share the screen. Okay. We can see you.
We can see you.
How to make him present, to allow presentation? He's able. Should be able to do that. This is the problem.
Andiamo?
Yes.
Enrico. sei?
Can you see my
Noi ti vediamo bene. Pensieroso, ma ti vediamo. Of his computer.
Yes.
Yes, we can hear you.
The green button on the bottom, share screen, green in the bottom, you see in the bottom of the Zoom, yes, green. Maybe it's a mobile.
Enrico, c'è un segnale verde sotto. Ok. Possibly.
I don't know, because when I share the presentation...
Well, just speak, just don't worry about the images, just tell us your idea to
Okay.
slides.
Oh, okay.
We can hear you.
So the point is that when just to pass the message that this new window just opened in the sky, which is polarimetry community of colleagues working on relativistic astrophysics. I mean, this is a real breakthrough, and there is something fancy in the history of these subtopics of X-ray astronomy that it would be nice to report to you. Let's say that you know that the X-rays were discovered by Röntgen in 1895, but he had fancy ideas about what the X-rays could be. But only 11 years later, Barclay, who was a student of Stokes, by studying the behavior of X-rays from polarization, discovered that X-rays are electromagnetic radiation. And when Giacconi and Rossi in '62 discovered the SCO-X1, immediately it was started some activity to perform in the future X-ray polarimetry. Actually, Bob Novick from Columbia, only 9 years after, made his first experiment to detect the polarization of SCO-X1 and of GRAB. So in the beginning, there was a fast, you know, the first satellite survey mission was launched on 70, that was Uhuru. And only 5 days later, and 6 years later, Ariel 5 and Ozo 8 were launched. I mean, only 5 and 6 years after the first discovery mission, the first polarimetry mission were launched. Then, after Uhuru, the Giacconi revolution, I mean, the use of optics and imaging detector in the focus, started, and eventually this was
okay. There is, please. You were saying about the Einstein telescope revolution.
polarimetry, but this was for 43 years later. Big feeling about the relevance of this, but this is not true. Because since the beginning, the best theoreticians started to image how polarimetry could be relevant in the case of X-ray astronomy, which is the domain of the non-thermal, also in case of thermal processes, the domain of asymmetry. And the real pusher of this discipline was Vitaly Ginzburg. Both Bob Novick and Hugh Bolt reported to me that they had started to work to build experiments of polarimetry, convinced by Vitaly Ginzburg that this would be the key to understand which was the role of non-thermal processes in X-ray astronomy. But the point were instruments. The only way that came out to be effective to measure polarization was Bragg diffraction. And Bragg diffraction is very, very inefficient system. It is billable if you want, but there is a good credibility. It's a robust method. But the best attempt was performed by Bob Novick and Rashid Sunayev with our modest contribution, because we made the detectors for this experiment, and Paolo Soffitta was doing his PhD thesis in those times, partially at Frascati, partially at Columbia. And this experiment, the PI was Rashid Sunayev, who was always one of the best supporters of polarimetry. But if you take, for instance, the best instrument, that was a Bragg diffractor. You start with a huge telescope built by Herbert Schnopfner in Denmark, with more than 1,000 square centimeters of collecting effective area. You arrive to an instrument with 10 square centimeters of effective area. But the original band is 15 kV, and the band of the polarimeter is 0.1 kV. I mean that in a technique that is starving photons, that needs photons because the statistic is rose against, you lose 99% of the band and you lose 99% of the effective area. So you start with the 10 to the minus 4, which is really a very bad start. So what was the change? The change is what we did when we really understood that this was not the way. The way should be photoelectric polarimetry. And this also, we must admit that also our colleagues in Marshall Space Flight Center, Martin Weisskopf and Brian Ramsey, and also in Italy we started, they were trying to use the light to image the track of photoelectron. We were working on the charge. Eventually, we get in touch with Ronaldo Bellazzini, a colleague of a National Institute of the Institute of Nuclear Physics in Italy, that was a big expert, and we worked to arrive one dimension, eventually in a real imaging device that was that could export the Giacconi revolution, the use of optics to polarimetry, and make polarimetry not only of a crab with 1 month and a half of pointing, but polarimetry of maybe tens of sources, potentially in the future hundreds of sources. And this, unfortunately or fortunately, was not a straight line. Martin Weisskopf was very busy to launch Aksap Chandra, and after the disaster of the Hubble, they were really very anxious, and we were very busy with this discovery of afterglows of gamma bursts. We should complain that this breakthrough of gamma burst has delayed the breakthrough of polarimetry. But honestly, we cannot complain because we amused a lot also in that. Eventually, this detector was ready. We proposed it 13 times to Space Agency. Eventually, we succeeded. First, NASA selected a competing proposal with a detector that was an evolution or an involution of ours from some American colleagues. Eventually, they failed to be compliant with the schedule. We were approved, and we have seen what Paolo and Fiamma has just shown to your attention. So my message is that pay attention, because actually many views in relativistic astrophysics may be modified by data that in many cases, I don't know whether they are the majority or not, but in many cases are significantly discrepant from which were our expectations. So this is my message, and I wish you a good work at this conference.
Thank you so much. Thank you so much. Beautiful presentation, Enrico. And I can only add one thing, that you observe polarimetry everywhere that we expected with enormous more detail. But you are also observing polarimetry in two cases, in the Vela remnant and in the Crab Nebula, which a priori we are not expected. And is telling us very much, to us relativists, the possibility that there are black holes creating this this X-ray emission, and therefore that there are many more black holes in our galaxy than we expected. This is one of the topics that we will keep discussing, but I already make to you all an invitation already for the next MG17 in China, in Beijing, to prepare now that you have the new data on polarimetry on all the existing sources, from SCO-X1 to Cygnus X1 to Cygnus S3 to all of them, to make a comparison, to take in 1 year time the comparison of what binary X-ray sources used to be and what it is from now on, and what we understand much more about the neutron star black holes. But of course, here at this meeting, we have enormous excitement, because not only Nanzang will be shortly here to discuss GRB 220101 and the beautiful data from NASA and Fermi satellite, but also we will have tomorrow arriving the people together with Nanzang, the people from the Terre observation of Lazo, which is by far the most incredible and fantastic observation ever in astrophysics. We will have a scientist from China to present. Of course, they have been published, but they will be presented here for the first time in real time to discuss with all of us. Thank enormously for your presence and your thought and your words and your splendid work that you have carried out through more than 50 years. Thank you so much again. I hope you realize this is an historical moment. I mean, historical. We are going back to all the classic work with new understanding and new details. And we need the presence of these people here to program the next actions. What we are learning more, and what the things conceptual more.
we were not expecting that we see the
different value organization that we expect questa è un'organizzazione large,
but organization where you not expect, because we're expected from the push, but not from the back. This is the people. We expect it from the pusher, not from the back. Okay. Yeah.
I'm not really I never had in my mind the physical picture about the mechanical I've always been but not I guess for example, we know that the I
or whatever.
I just heard that.
I also, for me, it's also a surprise.
somehow,
Yes.
when I put this, it goes...
No, not сверху. Вот эту.
Ах, вот это, окей.
Другую сейчас минуточку.
Нет?
Давайте попробуйте. Вот, все, работает.
No, it was back. Okay, this is up. Okay, okay, okay. Okay.
Все, работает?
Да, спасибо.
Микрофон работает?
Как это проверить?
Я, смотрите, Григорий, ты знаешь, как проверить, микрофон работает или нет?
Сейчас проверим, сейчас скажем. Да, все работает.
Да? Сейчас, когда я говорю, слышно?
Все работает, да?
Хорошо, спасибо.
And I have first to announce some important changes. The first speaker, Rashid Sunay, will be shifted to Friday will be shifted to Friday, will not speak today. Instead we will start with George Adolf, but I come to that in a second. And we have another change, this is at 5 o'clock this afternoon. Instead of our
Okay. So I'm going to talk. Okay. But, okay, I have this thing. Right. I am going to talk about some interesting phenomenon which we discovered, which you can understand from the title. I ask to excuse me for my hoarse words. I haven't yet recovered from a long trip from central Pennsylvania to Armenia. It's not that simple nowadays. So, okay, what is all this is about? First, I will say a few words about pulsar with nebulae. So if you have a solitary pulsar, almost all rotation-powered solitary pulsars emit relativistic particles, and in many cases, these particles are responsible for a substantial fraction of the pulsar energy loss. These particles interact with ambient medium, produce shocks. These shocks accelerate particles to even higher energies, and we can see pulsar with nebulae. Pulsar with nebulae, I must give a special thanks to Chandra because it was fantastic angular resolution, the best in the world. And thanks to Chandra, we now more than 100 pulsar with nebulae detected. Well, classical examples are the crab, which we have seen today, and another one, which was also mentioned, is yellow pulsar with nebulae. These pulsar with nebulae are in supernova remnants, and they move either with subsonic or transonic velocities, and therefore, the shape of the nebula says about angular distribution of the wind. Other examples, this is another beautiful example. It is Geminga pulsar with nebula. If you look at it, it has a quite different morphology. It has two lateral tails, central tail, and of course the arrow here, it shows the direction of the motion of the pulsar. And the shape of this nebula, which moves supersonically in the interstellar medium, is due to this supersonic interaction. It changes everything. It produces a tail behind, or trail behind the moving pulsar. And sometimes, in this case, these lateral tails are
band jets of a pulsar. At least this is what we think. Another very interesting example is the so-called lighthouse pulsar-width nebula. Here we see the pulsar, this direction of motion. Somewhere here is a huge supernova remnant, which is not seen here. But in addition to the more or less usual tail, we see what we call misaligned outflow of filament. These are leaked relativistic particles which move along the magnetic field lines of the ambient medium. So we see that there is quite a variety of different shapes of the pulsar-width nebulae. Now the question is, all these are solitary pulsars. What happens if the pulsar is in a binary? And it, of course, depends. Yeah, first of all, we are talking about non-accreting binaries, because accreting binaries, they simply quench the pulsar. We do not have all this. So the manifestation of a pulsar-width nebula would depend on the nature of the binary. If, for instance, it is a broad binary with slow orbital motion and with some star which is a dwarf without wind and so on, there actually will be no effect. It would behave like a solitary pulsar. If there is, for instance, and it is very, very usual case now, if it is in a tight binary with a white or red dwarf companion, then the pulsar evaporates the companion and we obtain a black widow or a back system. In terms of extended emission, we can see, I think, in two examples, simply tails behind the moving binary. But the story is quite different if it is the companion is a source of strong wind. In this case, the pulsar and stellar wind collide with each other. It produces shock. Which is called intrabinary shock. It accelerates particle and it leads to non-thermal emission in a very broad energy region. And there could be two cases. One case is when the momentum flux of the pulsar wind is larger than that of the companion, and vice versa. In this case, in this schematic picture, here is a companion, which is a massive star. Here is a pulsar. This is unshocked pulsar wind. This is pulsar wind termination shock. So basically, the shocked pulsar wind is beyond this surface. And in this case, the wind of the massive star, it pushes in the direction, pushes the pulsar wind. Now the binary rotates, and when the binary rotates, all this picture rotates. And basically it rotates around the star, because usually the star have large masses. So we, long ago, I think 13 or 12 years ago, we wanted to check how in reality would look such pulsar-width nebulae. Our assumption was that likely we would see simply extended emission, because when this thing rotates, some hot matter, hot relativistic electrons are thrown out of the binary, but it would go around the orbit. Or we thought that maybe if the pulsar has a jet, the jet would wind around the binary or around the central star, and we see something interesting. In reality, we see something different, maybe even more interesting. So now about the main part of the talk, it is a binary system which consists of the pulsar, and here are its properties, some middle-aged pulsar with relatively large energy loss rate, but not huge, more or less usual magnetic field. In the second companion is a massive Oort star, late Oort star, from which we see H alpha winds, and so it is source of the wind, and it has an equatorial disk which is inclined to the orbital plane, which is shown here. So basically, the pulsar goes like this. Most interesting property of it, which strongly affects the picture, is the high eccentricity of the orbit. It is 0.87, and its period is 3.4 years. So our first observation of this system shows the following. It shows just a hint of extended emission to the south of the star, crudely speaking. We were not sure even that it is real, but it was enough to propose more observation. You get some time. In the next observation, next cycle, we had 3 observations during, one before Apastron, the other one just after Apastron, and one more closer to periastron. And so this was the first observation, and here we clearly see the extended emission. It is here. This is the next observation, and this was a real surprise. This extended emission, or maybe it was another emission, we do not know, but it moved, it became separated from the source. It is not what we would expect from a normal pulsar with nebula. In the fourth observation, we see again this emission at even larger distance. So it means that some X-ray emitting matter is ejected from the binary. So these are just these 3 pictures. And of course, the first thing which we try to estimate is what is the velocity of this ejection. And this estimate gives a velocity about 0.1 of the speed of light. No, it doesn't work. Here is some. No, it doesn't work. Anyway, it's not scientifically not important, just to show the picture. In the next cycle, we got 5 observations of the source, and they are shown here. In the first observation showed nothing interesting. It's possibly just wings of the PSF. The next observation in the Apastron did show some structure. The fourth observation, it shows something really strange. It is like some brighter part and elongated in this direction, and some matter which is stretched across this motion, which we call whiskers. It may be not so well seen because the screen is too light, but in some pictures it is really beautiful. In the next observation, it showed one more strange thing. This matter became brighter. It changed its shape. It became brighter by a factor of a few. So what happens? Because normally, we would expect that if some matter is expelled, it should simply cool down and fade with time. But it was not the fact. In the last observation, now it is indeed faint. It is elongated and so on. So basically, this is the sequence of these images. It shows one most somewhat strange thing, like a second piece of matter, we call them clumps, appeared, but it is not quite clear. So now, what happens if we just plot the separation between the central source and this extended emission as a function of time? In this picture, vertical lines are the moments of epochs of periastron of this source. So first 3 observations are shown here, 5 observations are shown here, and if you just fit the first 3 observations with a straight line, it crosses the horizontal, the x-axis at time 0, and time 0 is time of periastron. So it looks like this matter was ejected in periastron. However, the second picture, if you do the same again, the linear fit, now it was several hundred days after the periastron. In principle, we of course can fit not with a straight line, but say with a parabola, and assume that, okay, maybe there is some acceleration. And in principle, no, we cannot exclude this, although I'm not sure that we can explain. This just shows how the fluxes and photon index vary. So a typical photon index is about 1.4. And this shows the evolution of luminosity. Now we had the next binary cycle, we had 6 observations. We expected to see some beautiful things, but in fact, it was a little bit disappointing, or not a little bit. Because yes, we see, I think that at least in this case, and certainly in this case, some extended emission, but it is faint, nothing very interesting, and in 2 cases, there is no even a hint of extended emission. It means that something happened. What exactly? It is a question. Yeah, if you now again play the same game, and for 2 cases where we did detect emission, estimate the separation, okay, again, if it was, clump was launched in periastron, there should be some acceleration, but it is not clear. It is not clear. No, I mean, statistics is very poor here. Now, a few words, what could it be? First of all, the most probable emission mechanism is synchrotron emission. We try to play, we tried to play with Compton emission, but it did not work. And some parameters are written here. Parameters are written here. Most likely what radiates the emission are electrons with TeV energies. Total energies should be about 10 to the 41 ergs. And the power is what is written there. So there is actually another problem. If you estimate a reasonable density of this clump and take the size, which we know, because the distance is pretty well known, and imagine that this clump, this cloud, moves simply in this stellar medium, then just the drag forces of the interstellar medium, they would stop and destroy it almost immediately. So it means that likely, well, there are different options. First, it means that likely some ions are loaded there. So it's not just poor electron wind. Second, it may be that they actually propagate not in the normal interstellar medium, but in some channel, which was somehow carved out by previous episodes of emission. So it's kind of a scenario may look like this. So we actually have this binary motion. Most part of the orbit, the pulsar, the, how to say, the momentum of the stellar wind, of the companion's wind, it pushes matter along this axis, that is along the apastron. And that is why all clumps are emitted in approximately the same direction, not around. If it were a circular binary, then we would see emission everywhere.
So most likely the clump, or at least it was a hypothesis that what happens. When the pulsar moves through this equatorial disk of a large star, where the density is much higher, somehow it perturbs the state of the disk, and electrons became mixed with ions, and all this structure, they move outward. Yeah, there was a numerical simulations. They are, of course, with some assumptions, not quite realistic, but basically the authors got a reasonable or similar quantities. So what there are, of course, some open questions. First of all, are indeed clumps launched around the periastron? Because otherwise it would be difficult to explain. But if they are launched not around the periastron, it means that they move with acceleration. If there is acceleration, what is its source? What actually provides it? Is this acceleration constant or not? We do not know. Also, we saw a clump brightening, a quite strange effect, what caused this brightening. What was the origin of this extended structures like whiskers? It was not clear. What was the nature of this second clump? It was also not quite clear. What was the reason of the suppressed ejection in one of the cycles? It is another question. Well, a natural attempt to understand it is to see what is going around the periastron. This source is known to be a gamma ray source. This gamma ray emission occurs it occurs not around the periastron, but occurs after the periastron. And this gamma ray emission, which is shown in the upper panel here, different colors show different years. And we see that it looks quite differently. Its behavior is different. And say in the periaster preceding to this low ejection, gamma ray flux was higher. And we saw that somehow it means that maybe the disk was destroyed by another mechanism, or there was not enough matter supplied by the companion. But in fact, in the very last periastron, which was in February 21, the gamma ray emission was particularly strong. These are these brown dots, and it was substantially after the periastron itself. So our idea was to somehow connect this suppressed ejection with dim gamma ray spectra. It did not work. And now it is the new cycle. We had only one observation in this cycle, and it is shown in this picture. And this observation is almost exactly the apastron. And we see pretty good, pretty bright extended emission. Apparently, it is some formation of the clump. And compared to the previous observation in the previous cycle at the same binary phase, it is much brighter. So we expect to see something much brighter than we see now. But for that, we should have our proposals accepted, which is not guaranteed at all. So here is summary of findings. I will not repeat them. And here is this possible interpretations. So thank you.
Thank you very much for this good presentation. Are there any questions? Maybe you take the microphone so people understand you.
My question is maybe childish a little bit. I want to know what's the real mechanism of producing basically one ejected piece per orbit. Usually what we see when we see ejection, we see many episodes of ejection
No, if you assume that this ejection occurs during the periastron, then during the periastron it is of course not a moment, but some time, but this time is short because the pulsar moves very fast close to periastron. So if it is indeed due to interaction with the disk, this interaction, it takes days or maybe weeks maximum. And then it goes goes further and it cannot produce anything. So this is the idea why it would produce only one clamp per orbit. But maybe it is wrong.
Is there any other question? I'd like to thank you very much.
Thank you. Can you please, можно его отцепить эту?
So next speaker here is Yusuf Kibuti, and I'd like to welcome here on the stage for the presentation of three argument concepts.
We cannot find your presentation, but let me put in the meantime.
Thank you.
Okay. Okay.
Did you get it?
Which one is yours? We just need to
Here
I
find article.
Is this PPT? I think no, wait.
Yeah.
Can you show back? Yes, this one.
PowerPoint.
This is the button. This article. Three arguments, okay? Is the folder, right?
Massive gravity?
No, wait.
No, just a minute.
Yeah. Okay. This folder.
Yeah. Let me turn it off.
This next, this previous, and this is laser.
Just a minute, let me see.
Try again.
Good.
One more.
Okay, thank you. No, that's fine.
Apparently there was this problem in Spain that they stored the computer to a ship, and he's trying to recover, and we present the talk on Friday if we succeed.
Am I begin? I'm afraid my lecture would be somewhat different from what you've heard so far before. And it's most of the lectures were the most recent reports of observations. Mine is one of the scrutinizing the very oldest concepts that one has in physics. I'm afraid my lecture is almost a textbook physics lecture today. You see, when do we begin? How do we begin Newton's equation? A mass m creates a gravitation gm by r, or an electric charge q creates a magnetic field qm q by r. There is an unwritten concept in what we're seeing, that there is a point with zero volume, but with finite mass or finite charge. This contradicts quantum mechanics. quantum mechanics tells that we cannot precisely define the position of a particle and put it at, say, for instance, r equals 0, and then work with it. It has to have some oscillations or fuzzy positions in the phase space. So, point-particle assumption is in contradiction with the principles of quantum mechanics. This is the point, the first point that I am objecting to it. This concept is singular and entails, let me see, how was I operating this? No. Concept, it's fine, all right. This concept is singular and entails singularities and divergences. It is in conflict with the founding principles of quantum mechanics, namely the uncertainty principle, that no physical entity can have precisely defined position and or momentum coordinate. Now, this is the first point. The second point, which I find it somewhat unusual, in Schrödinger equation, for instance, or in Dirac equation, you see electromagnetism interacts with the quantum wave function. But you don't see reaction from the quantum wave function on the electromagnetism. This is what I call asymmetric action of EM on quantum wave functions. If I may quote one sentence from Einstein, it is contrary to thinking in science to conceive of a thing that acts itself but which cannot be acted upon. You find this sentence from Einstein in his meaning of relativity. It is contrary to conceive of a thing that acts itself but which cannot be acted upon. Here, I would like to apply this criterion of Einstein to the action of EM that should be acted, if it acts on quantum waves should act on the electromagnetic field as well. In other words, one should see traces of quantum mechanics in Maxwell's equations. That's what I'm going to propose. Oh, Einstein's sentence is here. A la Einstein, I'm proposing a mutual action-reaction partnership between electromagnetism and quantum wave. By so doing, quantum wave shares its non-localized nature with electromagnetism, removes its singularities. Of course, quantum electrodynamics does this, but by throwing away, first of all, the concepts of quantum electrodynamics are very abstract, not easy to grasp, not easy to teach in high schools, but this can be taught in high schools. Pedagogically is much easier thing to do than the concepts you find in quantum electrodynamics. The next one, conventional U1. Conventional U1 symmetry leaves quantum dynamics invariant under a general Lorentz gauge and imposes the standard minimal coupling of quantum waves to electromagnetic four vectors. That's what you say, the standard recipe is that if there is electromagnetism on quantum process, put P, the momentum, P minus E times vector potential. That's the recipe that one follows and one gets the minimal coupling of electromagnetism to to quantum waves. But if you read standard electromagnetic books, say Jackson, for instance, you arrive at a sentence that, in spite of the general Lorentz gauge, there is also a restricted Lorentz gauge. The gauge function you are introducing, its nabla should be equal to 0. And if I want to ask for U1 symmetry to hold under restricted Lorentz Lorentz gauge, then this invites in a coupling. Let me see. One, however, has the option to ask for invariance under restricted Lorentz gauge. If I insist on invariance under restricted Lorentz gauge, this invites in a coupling of the derivatives, a coupling with the derivatives of the vector potential. One should find this term in it. So this is my third point that I'm trying to emphasize on it. 3 points: to throw away point-particle assumption. Secondly, to insist on mutual action-reaction between electromagnetism and the quantum waves. And thirdly, expand U1 symmetry to include restricted Lorentz gauge as well. Let's see how one can do this. This is a Lagrangian. Oh, I'm sorry. This is the Lagrangian, first term. Second term is the free Lagrangian for Dirac wave. This is free Lagrangian for the electromagnetic wave. Psi bar A mu psi is the minimal coupling term. Psi bar d nu gamma mu d nu A mu, derivatives of the potential, is the extra coupling, extra to minimal coupling that I'm introducing. And so I'm going to work with this. These are the last two terms are interaction Lagrangians. Free Lagrangian for Dirac wave, free Lagrangian for electromagnetic, and the other two terms, interaction terms. Now, from these, I can ask for Euler-Lagrange equations for psi as well as for A mu. This is a Dirac equation with minimal coupling and with the new coupling that I introduced. This is Euler-Lagrange equation for electromagnetism. This is Maxwell's equation equal J mu, but J mu has this psi function here. Therefore, you see psi in Maxwell's equations. Now, these equations are invariant under this transformation. This is a U1 symmetry. If I change psi to psi bar exponential I e kappa chi, change A prime mu plus derivative of A kappa, provided del mu kappa equals 0. This is restricted Lorentz gauge. Then these two equations remain invariant. Let's see if we can solve these. reaction of quantum wave on electrons' own electromagnetic field distributes the electron charge current density. By solving that equation, by solving this equation, electron charge is distributed. In ordinary Maxwell's equation, this is delta function, E times delta function R. It's already distributed. Electron gets distributed charge. Now the rest of the story is very simple. If electron has distributed charge, and if it has spin, therefore it has an electric current associated with it. Therefore, there is a magnetic moment associated with it. Therefore, there are anomalous G factors associated with it. These are the consequence of this equation. The consequence of solving this equation is distributed charge for electron, distributed current for electron, therefore magnetic current, simply because it is spinning. Therefore magnetic current, and therefore a magnetic dipole moment in the first approximation, and therefore anomalous G factor to go with it. Anomalous G factor is one of the most precisely determined physical quantities that you can find. Both QED and laboratory measurements give anomalous G factor of electron with a precision of 10 to the minus 12. So I proposed something, and at the next I'm going to elaborate on G factor and see if the G factor I find, how much produces the laboratory measured ones and the QED predicted ones. I already narrated these. Electron has a spin. A distributed spinning charge means an electric current, and thereof an ever-present magnetic moment to go with. This is regardless of whether the electron is exposed to an external electromagnetic field or not. This is the interaction of quantum wave of the electron with the electromagnetic property of it. I'm not saying that, I'm putting electron in an external electric field of, say, proton and hydrogen atom. Single electron interacts with itself. There are two fields associated with the electron. The one field, electromagnetic field, the other field, the quantum wave field. I'm asking these two fields to interact with each other. G factor, let me go back to my initial equation. There were two parameters here, Z, you see here, here, and here. This is a coupling factor. I haven't talked about it yet. And there's a second kappa. It is also a second coupling constant. Don't worry about these alpha A0. These are introduced simply to make the dimensions of these three terms to be consistent with. And this is what do you call it? Fine structure constant. And this is what's it the name? I forgot. Bohr radius or something. Bohr radius. It is Bohr radius. Now, so if I put kappa equal 1 and z equal 1 over pi, the g factor becomes this up to alpha by p squared. Of course, I forgot to mention, to emphasize that the Euler-Lagrange equations which I had, they are very much nonlinear and coupled. The linearity of Maxwell's equations is lost. The linearity of Dirac or Schrödinger equation is lost. Therefore, we are dealing with pairs of coupled and nonlinear equations. I have solved these things in the first iterative approximation, namely assuming that let's go along with the ordinary way of doing things, and then solve Schrödinger Dirac equation, put it in Maxwell's equation, get the new field, and for the second round of iterations, go again to the Maxwell's equation, and so on and so forth. In my first iteration, if I put kappa and z, which were undetermined, equal to these values, anomalous G factor up to this factor alpha by p squared becomes this. The QED theorized and laboratory measured G factor is this one. The difference is this much, but this is not the QED. This difference, this term is not totally QED value. There are other contributions to it from strong interactions. So I think, at least to my own satisfaction, I have produced the G factor up to this moment of the term. And in the first iteration, if I go back and do the second cycle of iteration, I'm expecting to get alpha by p to the third, alpha by p to the fourth. And also I have a hunch that the first, the odd powers of alpha by p will be the Z coupling, kappa coupling will be responsible to it. And the even powers, Z coupling will be responsible for it. And let me see. I have two historical remarks. In this expression, G factor alpha by P is Schwinger's 1950 QED term. Dirac's G factor is 2, period. Schwinger in 1950 through QED obtained this one. Alpha by P squared was weren't at the time known, and Landau, not Landau. In 1940s, Pauli obtained alpha by P squared term. Pauli introduced extra EMQW coupling as the coupling through F mu nu. F mu nu is antisymmetric derivatives of the vector potential. In Pauli's introduction was correct, and it was given the alpha by P squared term correctly. But the root of it, that it is coming from the restricted Lorentz gauge, was lost because in this antisymmetric derivatives, one does not see that Laplacian of that chi should be equal to 0. Sakurai calls Pauli's addition as an ad hoc introduction and dismisses it as an unnecessary complication, for whatever it may be worth, these things. In our first iteration, the odd power of alpha by pi in the G factor comes from the minimal coupling. It is actually a noder charge. Any symmetry, we know that has a conserved quantity to go with. In the context of Noether's theorem, we may call those constants Noether charge. This alpha by p is a Noether charge. Alpha squared by p is again a Noether charge coming from the coupling beyond the minimal coupling. And if I suspect the pattern to repeat itself, even powers of alpha by p to go with minimal extra coupling, and the odd power, even powers with minimal, odd powers with minimal, even powers with extra coupling, which I had introduced. Thank you.
Thank you for this interesting contribution.
Before you, sorry. I've done this for electromagnetism to remove the point particle singularity of a point charge. The same problem exists for the gravitation. You see it in Newtonian field, you see it in Einstein field, you see it in Schwarzschild metric, you see it in the Kerr metric. In fact, the what you call the Schwarzschild singularity at R equals 0. Intrinsic singularity, we call it. The singularity of Schwarzschild metric at R equals 0. What's the common word for it? I forgot. No, at Schwarzschild radius is the coordinate singularity. At R equals 0, what? Essential singularity. The word essential. Thank you. Essential singularity comes from the fact that we are working with a point particle singularity. When we say if a mass shrinks to smaller and smaller volumes, we are saying that we are reducing the size of the phase space. The size of the phase space, the size of the configuration space, the volume reduces it, and also the energy space reduces it, and the phase space is becoming shrinking and shrinking, then quantum effects should be introduced in it. So the same thing can be done for to remove the essential singularity of the black holes, and this is our next project. It's not finalized yet. Thank you. Sorry.
Can I ask a question? It was mentioned that quantum fields do not influence on electromagnetic fields, but it is well known that if we write down classical Maxwell equations with current density on the right-hand side of these equations, and we take medium value, we obtain right equations in quantum electrodynamics. And it follows that current density and therefore quantum fields influence on electromagnetic fields. And what means you
I did not say quantum electrodynamics, this replacement for, I did not say quantum electrodynamics is incorrect. Quantum electrodynamics is one of the most precise theories of physics, all right. But what I'm saying, the concepts there, they are very abstruse, difficult to work with. I'm a teacher. I am a lifetime teacher. Pedagogically, this is much easier to tell to even high school students. But you cannot introduce quantum electrodynamics to high school students. That's what I'm saying. And also, no one has so far said that the point particle singularity is no physical concept. No one has said this explicitly. Point particle singularity is non-physical concept. That's what I'm saying here. Quantum electrodynamics is fine. I have no objection to it, but it is difficult.
Is there any other concept of particles?
Yes, there is one logarithmic singularity in QED, and people do it away with very complicated terms. Again, when I'm applying these things to gravitation, even in my approach, that logarithmic singularity still persists. I've been wondering whether it is a physical concept that we are somehow are not understanding it, or it is a mathematical concept, the theory of numbers. If you remember the theory of numbers, the zero in theory of numbers took 500 years to get accepted as a physical entity. I'm wondering whether we should ask mathematicians to reconsider their numbers, number zero, and help perhaps physicists or not. That's a philosophical point. Please.
I'll be brief. So my doubt is your comment about gravity sector. So as you know that in that case there is gauge choice is very difficult. Like here you have gauge boson, but there it's very difficult unless you restrict the local frame. So I understand your extrapolation, as you said nicely, that it could be extrapolated from gravity as well. But those issues with gauge and other things, unless you restrict to local frame, I don't know how to tackle this. It's like a coupling what you have described.
If you have time, let's talk later on some more. Okay? Thank you.
Okay, now it's another question. Thank you again.
Thanks.
Thank you very much.
Sorry?
And this is the presentation which has been planned for tomorrow, titled Future Wave Telescope Related to the Mighty Wavelength Context. You ready?
We are getting ready.
Almost.
We don't have a port. We don't have a port.
May I connect this?
Oh, yeah.
Sorry.
We don't have port. Yeah, because it's a bit heavy. So this is the, do I see transcend? This is transcend. This is it, right? I think that's it. Yeah, I think that's it.
Yes, this is.
Let's see if I call it Pian Zeldovich. Yeah, it's there.
Wait a minute.
It's finishing. So slow? It's very slow. 24, 25. Yeah, it's finished. Yeah, it's finished. Yeah, I think we have, yeah, I think there is everything. Okay.
This next, previous and laser.
Okay, so, okay, thank you very much. Thanks a lot. I'm sorry for the technical problems. We had to find a port to allow my presentation to be shown. So we will switch gears a little bit. This presentation will be eminently observational, and in fact, I will speak about, everybody can hear me well, yes. I will speak about an experiment, a big experiment, a big project that is coming up. In fact, it's already working, partially working, and when it will be a fully fledged project, it will be an extremely powerful experiment in the TV, in the highest, very high energy domain of the electromagnetic spectrum, the Cherenkov telescope array, which is not the big jump with respect to the past, is that the Cherenkov telescope array is not a single dish Cherenkov telescope, it's not a stereo system, it's a multi-stereo system, it's an array of many Cherenkov telescopes, which are essentially optical telescopes, because the Cherenkov light is blue optical light. And they will, thanks to the big area they will cover and to their number, they will be extremely sensitive. They will allow an extreme improvement in the sensitivity of the detection at TeV energies and in the angular resolution of their detection, so of the localization of the TeV emitters. As we know, TV science, TV energy astronomy, unlike optical astronomy, unlike every other electromagnetic band, is still a pioneering science. Pioneering in the sense that we know an extremely low number of sources. We are at the level of 250 sources known. 1/4 of them are not identified. We can have guesses, good guesses, but we are still identifying a large fraction of these. What we know so far about TV sources is that most of those, here you have the TV map of the sky. Most of the sources on the plane are, of course, galactic, are of galactic origin, and you can see some, these are color-coded. They are pulsars, supernova remnants. Virtually all of those outside the plane are extragalactic, and they are blazars. A couple of extragalactic TV sources are star-forming galaxies. They are extremely nearby. We are starting detecting some gamma ray bursts. They are so far a handful, those that are TV emitters. Most of the others, all of the red balls you see in this map are blazars. And so the Cherenkov telescope array will determine a big breakthrough in this wisdom, in this current knowledge, in that, as I say, it's an array, so the shower comes, it's spread over a vast area, so many telescopes are detecting it, and it will be possible to reconstruct the origin of the shower with sub-degree, in fact, fewer minutes for bright sources, angular resolution. The full array will consist, as you know, of telescopes of different sizes. These are all optical telescopes, and their aperture may seem whopping to you, and in fact they are, because the LST, the large size telescopes, which are 8, should be 4 in Chile and 4 in the Canary Islands. The Cherenkov telescope array will cover both hemispheres, are 23 meters, which is very big for an optical telescope, but as I say, these collect Cherenkov light, meaning they are less refined, less polished than the real optical telescopes. Then there will be a few dozens of medium telescopes, 12 meters aperture, and some small telescopes. These are supposed to be only in Chile to observe the Magellanic Clouds. In Europe, we are building a twin system of small size telescopes, which is the ASTRI mini array, which is going to the Canary Islands, and I will mention a little bit later. So we will focus here, our interest here mainly is on, obviously on TV transients. Most of TV sources are in fact transients. And so the idea in this talk is to provide the necessary support at lower energies to detect these sources, not necessarily only explosive, but those are the most interesting. Follow them up at all wavelengths and possibly go and sample the fastest, probe the fastest time scales. So this talk will be actually on ground-based radio to optical coverage of these TV emitters through 4 facilities or modes. We will be more specific, that are funded specifically in support of the Cherenkov telescope array as part of the post-COVID recovery plan that Europe is funding through the Italian Ministry of Research. The program is called Cherenkov Telescope Array Plus, and we have 2 years to complete it. In this particular sub-package of the CTA Plus, we will be dealing with a large field of view polarimetric camera, a fast photopolarimeter, an improvement of the radio receivers of for the VLP, for the very large baseline array interferometer, and an experiment that uses the small telescopes themselves for optical purposes, for interferometry, intensity interferometry, not phase interferometry. The motivation is obvious to do polarimetry, especially for blazars. Polarized light at all wavelengths may have different origin, there may be different reasons why light is polarized. Some are intrinsic reasons, the presence of magnetic fields over a range of strengths. The radiation may be scattered, and the scattering produces a privileged direction, or the geometry. Polarization sometimes probes the geometry itself of the emitting region. So the first experiment, the first camera I would like to talk about is this polarized camera for the VLT survey telescope. The VLT survey telescope is a 2.5 meter telescope, which is in Paranal, at the same location as the VLT array, the 4 units of the VLT array. And it was supposed to produce, it's a large field of view, it has a large field of view camera, presently, Omega Cam, which is supposed to detect sources and feed them to the VLTs for spectroscopic follow-up or polarimetric, sophisticated follow-up. It has changed, this VST has changed hands. It's no longer, it is still obviously physically in Paranal. It will not move from Paranal, but it has changed management. It returned to Italy. So Italy is now managing the programs, and our idea is to couple to Omega Cam will not be removed, but it will work together with this VST pole, this polarized camera, which has these are the specifics, the technical specifics of the camera. Without going too much into the details, it is important to remember that this camera has a large field of view, so it can be coupled, it can do polarimetric surveys or follow polarimetric in total light surveys like the LSST, it can work together with instruments that are performing total light surveys. Polarimetry will be optimized in the, let's say, 6,000 R-band, between R-band and V-band range. What can we do? Well, as I said, from the without focusing, for lack of time, too much on the galactic domain, the most important extragalactic sources are the blazars, as I said, just because they are so many and they are so bright, and so bright at TeV energies and so numerous. As a matter of fact, all blazars are virtually very strongly polarized, because that's by definition, and it's the defining property of blazars is strong polarization. We are talking of polarization at the level of 30, 40%. What are blazars anyway? Well, you are certainly familiar with these beautiful, spectacular radio images of the jet of M87. This is seen in various scales down to the core, to the heart of the AGN. Blazars are those objects, are those radio jets like M87 that we see at small, very small angle with respect to the jet axis. This is seen perpendicular to the axis. Blazars are those for which we don't see actually the jet because it's pointing very near, very close to the line of sight. This is the typical spectrum of broadband spectrum of a blazar. This is a very famous one. It's very close by. It's the first, in fact, with Markarian 421, it's the first. Those are the two twin blazars that have been first detected, the TeV energies. These are among the strongest TeV emitters in the extragalactic domain, also because they are so close. Markarian 421 is at similar redshift. And they are both extreme synchrotron blazars. The first peak that you see here, this is a nu-F-nu representation. The first peak is of synchrotron origin. The second one is a bit smaller because of the very strong Klein-Nishina suppression. The TeV spectrum here has been corrected for background, for the far infrared background. This is corrected. But still, it is smaller and very steep because of the Klein-Nishina correction, which is, of course, an intrinsic effect that you have to take into account, that is, you cannot correct for. During flares, this synchrotron peak goes up to 100 keV or more, and accordingly, the TeV flux brightens very much. And this is one of the best candidates for polarization. This is one of the first objects we will try to observe with VST Pol in optical polarization. As we've seen this morning, this is also one of the first sources that were detected in X-ray polarized light by ICSP. There is this, this is the long-term variability on the left of this source at various wavelengths, including the polarization, actually, sorry. This is the polarization degree. And here is the spectrum, the polarized multi-wavelength spectrum that Paolo Soffita has already shown this morning, radio, optical, and X-ray polarization. And here is the time profile of the polarization, which shows no significant variation of the X-ray polarization, which is thought to be consistent with a certain model, a certain scenario for the shock profile, shock accelerated, energy stratified electron population model. Sorry. This is another example where the polarization helped reconstructing the broadband, not only the broadband behavior, but also the geometrical development of the flare. You see here the beautiful, these are four the light curves of this object. BLAC is the prototype of blazars. And the two lines, the two dashed lines here highlight a couple of flares that are blown up here on the right. And as you can see, there is a very strong, beautiful, very neat variation, rotation of the polarization position angle that is correlated with the crossing of an upstream radio blob, the development of an upstream radio blob. That's the region where the plasma is still being accelerated. During this development of this blob, the first flare occurs. When the blob crosses the standing accretion core, meaning the area where the acceleration stops, you have the development of the second flare. This arrow here indicates the crossing of the blob. This is the blob that is moving superluminally. It crosses the standing accretion, the standing shock core. This is not the center, necessarily the physical center of the AGN. It's the area where the plasma acceleration decelerates, stops. And this is geometrically the geometry of the source of the AGN is reconstructed in this figure. You have a helical magnetic field that produces the rotation of the position angle of the magnetic field, and then the standing shock thereafter. Polarization is also a red herring for gamma ray bursts. It's very telling that there is a very strong degree of polarization in gamma ray bursts. It is very difficult to measure it because it's highly variable, and it is best measured during the first epochs. Here you see Ringo. Ringo is a polarimeter that was on the Liverpool telescope, has been dismissed. There is a first detection a few hundred seconds after the explosion, and then it's no longer detected, unfortunately. This is a TeV gamma ray burst, by the way, one of the few TeV gamma ray bursts. And this is the famous, this is also a TeV gamma ray burst. This is the boat, a gamma ray burst that we will probably hear more about during this conference. This is unfortunately not detected in X-ray. There was an X-ray polarimetry attempt, but those are not, so on the left you see the profile, the gamma ray profile of the source, the beautiful bright gamma ray light curve of the gamma ray burst. On the right you see some XP, X-ray polarization measurements, attempts. Those are not detections. Those are different estimates of the background. Unfortunately, there are just upper limits, but I'm sure one can do better with a little bit more luck in the future. That was a very unfortunate gamma ray burst because it was extreme, it was spectacular, but it was behind the galactic plane, so it was quite hard to follow. More in the optical than in the X-rays, but anyway, this circumstance hampered a little bit the campaigns. And this is finally the first attempt, the first and only attempt of optical polarimetry of kilonova, the only one we know of, which is, it's not polarized, not significantly. It's consistent with the foreground. The 0.5% that you measure is consistent with the foreground polarization, which also may give you an idea, a hint of the geometry. If you have a good model of what you expect polarization-wise for kilonova, lack of detection may give you an idea, may give you a hint about the orientation of the system. In this case, for example, the system, we know that the system was seen significantly off axis. So probably the lack of a polarimetric detection is consistent with this. We don't see down the non-thermal jet. The non-thermal jet has a different, is oriented like 20, 30 degrees away. So probably lack of polarization is, lack of detected polarization is not inconsistent with this geometric scenario. This is the fast polarimeter experiment that we would like to implement. This is for the Canary Island, for the 3.5 meters Telescopio Nazionale Galileo. what we would like to do, well, this is a fast polarimeter, meaning sub-second time resolution. So we want to observe very bright, very compact sources. One example is this, it's quite rare to do this kind of experiments, meaning correlated simultaneous X-ray and optical measurements of the early counterpart of a gamma ray burst. Here there is an example of an extremely nicely time-resolved optical light curve of the optical flash accompanying a gamma ray burst. This is what we would like to do, potentially also with polarimetry, in optical and infrared. And this is another example of even more cutting-edge science, meaning the detection of optical or more probably, well, we don't know, optical infrared rapidly variable counterpart of a fast radio burst. As you know, there is no such detected so far. We know these fast radio bursts can be X-ray sources because only a single one, the galactic one, has been detected in X-rays. Unfortunately, there is no optical detection to a limit that allows us to say that it may, if there may virtually be no single component that connects the radio to the X-rays because the optical limit is lower than the interpolation of the, with a single power law of the radio and X-ray emission. This is done with a timing experiment at the Asiago telescope, and we will, with the ACFAP, we will do probably better than this. This is our effort in radio. We don't build anything new here. We just want to implement new receivers because the area of the collecting and radio antennas in Italy is quite competitive. It's quite good. What's not really competitive at the time is the band of the radio receivers. So we want to become stronger in that aspect. This gives you an idea of how we will want to improve. So now and when the CTA Plus experiment will be finished. It will be a much broader, wider radio coverage in the gigahertz domain, where most of the compact, both galactic and extragalactic sources are bright, are radio loud. And this is a variety of science cases that we can cover, including many things that have been discussed so far. And perhaps very importantly, gamma ray bursts. I'm giving a couple of examples of very important coverage that the radio VLBI observations have allowed for the TV, on the left, for the TV gamma ray burst. So there are radio detections that show an extra component with respect to the homogeneous thin synchrotron that connects optical and X-rays. And on the right, the real breakthrough of VLBI in the radio in gamma ray bursts. This is the first ever direct detection of a radio jet in a gamma ray burst. In radio galaxies, in blazars, well, M87 radio galaxies, you see beautiful kiloparsec jets in radio. You can resolve them, study them with accuracy, with great detail. Well, so far there was no such in gamma ray bursts. Nobody had ever seen a jet. There is only indirect, very strong, very compelling arguments for the presence of jets in gamma ray bursts, which are energetic arguments. There was no single detection. This is the detection of superluminal motion of the bright radio counterpart of a gamma ray burst, which stays confined and unresolved. It moves in time, it has this projected superluminal motion in the sky, and it stays compact and confined, meaning what we are seeing is the moving head of a jet, not an expanding sphere. We are seeing an asymmetric, an elongated object that moves. with considerable superluminal velocity, superluminal speed, which is very similar to the superluminal speed you observe in radio galaxies. It's quite comparable. And finally, stellar intensity interferometry. This is a rather peculiar system. This is not something that we would like to do to observe TeV emitters in the optical. This is using TeV telescopes, Cherenkov telescopes, which are optical telescopes, as I said, to perform interferometry. Not phase interferometry, it's the intensity, it's the second order of light that is going to be correlated. From many telescopes, you can use two, but you can use, of course, the more you use, the better the angular resolution, and that's what we would like to do. You essentially count photons and correlate them from different telescopes, and you reconstruct the image to a certain degree of precision depending on your baselines. This is an aerial view of the small telescope array at the Canary Islands. This is not Chile, this is the ASTRI mini array, which is composed of, at full regime, it will be 9 small telescopes. They are identical to the small telescopes that will go to Chile. The idea, this is a secondary use of these telescopes, which are not optimized for optical observations, but that's not, in fact, not a drawback for this kind of science. You don't need, for intensity interferometry, very accurate image, a very polished optical image. You just need the intensity. You use these objects, these telescopes, just like funnels of light. You need to just collect the light. And this is a gallery of examples of what you can make when you go to sub-milliarc second. You can go, in principle, to several dozens, 100 micro arc second with this kind of technique, which is a very old, the theory of this technique is quite old. It's been pioneered by Hamori, Brown, and Twiss, and as you see, the paper is almost 70 years old, the first paper. It is just, the difficulty here is to have a fast photometer. You have to count the photons in a very, very rapid way. That's the technical hurdle. Okay, and I leave you here with my conclusions about our attempts, about what we are doing for CTA these days. Thank you.
There's a question. Yes, let's see the question. Is it true that we can invest also in LSP?
Yes, yeah, yes. In fact, the big, this package, this is the package I am leading. It's like 5% of the total envelope. Most of the money of CTA Plus goes to build 2 LSTs.
You didn't mention the record with integral of polarization of more than 70% in Cygnus X1. Is that something in some way real according to you?
Cygnus X1 is an extremely bright source. I have no reason to doubt that. Maybe Paolo Soffitta knows this hard X-ray polarization detections better because that's his bread and butter. I have no reason to doubt Cygnus. There have been many reports on gamma ray burst, hard X-ray polarization, and those are much more flaky. But this one, this is a persistent source. It's the brightest source in the X-ray sky. I think it should be.
Because it was detected by 2 instruments. So this is why. So that would come from the jets, this polarization. Very close to.
It's quite high. It is quite high. It's quite high. So you need very, yes, it's almost a theory limit. It's close to the theory limit of polarization. So you need a very coherent, I would say, non-thermal process mechanism to do that. Yes, it's very suggestive of, yeah.
The other question is the funding for CTA solid?
Let's hope. It's a huge consortium. it's a very big consortium. So yeah, let's hope. Yes, it will be slow. Sorry, it's not. It doesn't happen. One large size telescope already exists, besides the medium and small. One large exists, and I'm told, I haven't seen the paper, I'm told the paper is already out of observations with one LST. It will be a slow process. You know, you need, it's a viscous, every time you have a big consortium involved, it's viscous processes, plus it's a lot of money. But yes, it will happen. It will be, at the end,
I just want to know if there are other sources with such radio brightness like Fifth Zeldovich.
Yeah, you know, the thing is that, for example, in blazars, when we do multi-wavelength spectra of multi-wavelength spectral energy distributions of blazars, for example, there's always a radio excess. At radio wavelength, there's always excess emission with respect to a homogeneous single component thin synchrotron. It means synchrotron is not homogeneous. In these sources are not homogeneous. They are extended, so there are different emission components, which are quite difficult to model, in fact, because you need a lot of parameters. It means that the radio emission comes from further external regions, which are different than the more compact emitting regions that produce X-ray and optical, and TV. So the radio usually comes from external, less compact, let's say more extended regions. They are still compact in a relativistic sense. But yeah, they are more extended, yes.
In the blazar part, you mostly talk about BL, like as you said, prototype of blazar.
Yes.
However, as you know that FSRQ is also another candidate, and particularly which also is showing optical, spectrum. I'm a little worried about you also for BL, you have calculated. I mean, you have inferred accretion rate 10 to the power. I think how much? I mean, 10 to the power. I think 20 gram per second. If I convert your unit.
Yeah.
But that will not be case for FSRQ because it cannot produce optical then. And also polarization. Can you make some comment about these two? I mean, one is polarization as opposed to what you are showing for BLAG, and second is accretion rate. That cannot be that low for FSRQ, otherwise it cannot be shown optical.
Sorry, okay, this one. So, polarization is here. Sorry, the left and the right panels here do not show exactly the same things. These are total light curves, X-ray flux, X-ray spectral index, optical and radio. Here you have the X-rays, the optical flux, the position angle of the polarized flux, and the percentage of the polarization. There is no obvious, this is true of BLAC and is true of other blazars. There's rarely obvious correlation between polarization, let's speak about optical polarization because in X-rays there's just one example, but which doesn't vary. The variability in optical total and polarized flux is very complex, very difficult. It's never clear. But it gives you important geometric information. Accretion is difficult to do. Of course, outbursts are episodes of enhanced accretion. That's what we know. In the fine details, again, are very difficult. What happens, the interaction between the accretion disk, the ergosphere, it's very complex. For sure that you have something that enhances the passage of a blob, enhances the accretion rate and produces this flare. Where the blob passes, you don't know. Does it pass does it produce accretion, enhanced accretion, when it passes through the upstream region of the plasma acceleration, or when it passes the standing core? This experiment seems to suggest that you have two episodes, two flares, one before and one after the blob that you are following with radio interferometry, before the blob crossing the standing accretion, the standing shock. So by the time the blob crosses the area where the plasma decelerates, it has produced two flares, one before and one thereafter. This is a very nice experiment. I wish we could do this more often. It's very difficult because you need very close by, very nearby blazars that are undergoing large variability.
Okay.
Thank you.
Thank you again. I suppose to make a break until 5:10. Is that okay? Half an hour? Yes. Yeah. And then the next speaker is waiting on the screen. Let's try to be in time back here in the room. Yeah.
No. I need it. What laptop is that?
Yes, I have this goes to my computer.
Not this one. Oh, I got it. Show me your laptop.
Yeah.
Try to find the solution. Here, just this one. Work fine. Yeah. I need a video. Can I open?
Yes, sure. This is computer is new for me because mine was broken completely.
Good. Congratulations on your laptop.
And actually they gave me because I said well, it was for visitor for 1 year.
I think we can turn this off.
Can I go there?
Yeah, of course. You can put it here. Григорий, простите, если нормально, что я отключу? Я просто...
Просто он онлайн тут?
Да. Вот, кофе дают. It worked.
Let me see how it works.
If you want also, I can connect this one.
Yes.
This one. This is not working. I forgot to turn it on. Great, it's working.
Okay, let me see how it works. This is to go.
Previous.
This is previous.
This is next, and this is the pointer. The upper one. Not this one. Yeah. Just a slow one.
Let me see all the slides.
Yeah, of course. Great. It will, no, any problem will be.
Okay, so it's very nice.
I can turn this all off and take your laptop.
Okay, thank you very much.
You are welcome. Can? Bana bir laptop var uzun tutuyor. Tamam, thank you. Yes? No signal.
Excuse me, one question.
Yeah, of course.
Is there, do you have a
separate microphone?
No, a electronic address that I can send.
Email address.
Wait a minute, I will ask.
If you could
Zeldovich,
clearly, so because I'm not used to this, just in case I make a mistake. It's good that you have a file, a PDF file.
I will ask Gregor and tell you.
Okay, thank you. Thank you very
Second.
much.
Mailina, Zelting Mailina, that.
Are you talking now or?
No, tomorrow. No, I was trying because this is a used computer, but it's new for me, so I wanted to be sure that I can manage. Yeah. Yes, I wanted to ask you about what type of dwarf galaxies you have seen AGA or black.
There are galaxies which have optical properties are classified as dwarf, and in some fractions yeah. There are like a little small galaxies. There are some very rather compact with small size, with a mass of 10
هذا دقيقة سكسلا عندك تنخلص مسموح لي Can you hear me? Neutron.
Okay, so they're not very distant galaxies. Our sensitivity is insufficient. So there are four galaxies which are unusually extreme. And then, so we say, okay, so these are targets for more detailed investigations, and for some of them are difficult in this, and using broad lines, etc., etc. So then, having supermassive black hole, which is active and increasing, and yeah, more than paradigm is that these four galaxies may be so there are pretty initial black holes in there.
Cuma bana internet dünyası bana ne? Operatör ne?
You can try to construct the large distribution of species. This is it's not published yet. Then of course, yeah, and these galaxies, they are very important for people doing black hole formation. Statistics, of course, Mars X-ray data is not sufficient. But at least we say some targets we should be able to explore classification. I have already, actually, I want to buy an extra ticket for the dinner, and I need to get some cash, so I'm pretty good at that.
İnşallah.
to be part of the lock, but I can everything seems good.
Okay, thank you. I think it may be a problem. I don't know. I think there is a delay of a few seconds between my speech and when this broadcast on the screen. I don't know if you.
Well, no, I mean the video is in sync with the sound. I wouldn't know about the delay. The thing is, if you have a return, like a feedback on your, that may be another problem. I don't think should be a problem. But maybe we have someone from the organization that can take care of that in a few minutes when they come back.
Well, I couldn't hear you well.
Hey, hi. Do you hear me?
Yes, I can hear you.
It seems there is no any delay. If you are talking about audio video delay, seems it is okay. Just can you move the mouse?
Okay, because let's see if I now. I am watching a film by the YouTube channel while connected to the Zoom. The point is that, for example, in the Zoom here.
But he's following from YouTube, no?
Hi, Yerevan.
Hello. Yes. Carlos, are you connected through Zoom or from YouTube?
Seems that this is no, the point is that from Zoom, I was only watching at the audience, not at the slides. That's why.
Yes, you should be in Zoom only. Okay.
Okay, then I will turn off the YouTube. So good, but if you listen without any delay, it's good. Because but let's see if it is synchronized when I change my slide.
Yes, let's see.
So, are you watching now are you changing? So, my slides are changing now for you as well?
No, you didn't share the screen apparently, no? Or you did?
You are sharing, yeah? I am sharing.
We can see only part of your screen actually. I don't know why.
Okay, I will do it again. So sharing.
Okay, try to share again. Yes.
And then,
I am changing now slides, but I think you are not seeing.
Can you put a full screen, your slides full screen?
Well,
Okay, better, now better. Still not full screen, but we can see it, the slide, yeah.
But why? Because it's the window. Okay, wait. I will share the full.
Yeah, exactly. You share the full screen, and then we will be following.
Let's see. Yes, maybe I missed that part. I will do it again. I was sharing only the window. That's why. Okay, let's see now. Use desktop capture. Okay. And okay, sharing full. And now let's see. Oh, wait, why now? That's not let me.
Nothing happened. Okay, now it's full screen.
Now it's full.
Yes.
And Gregory, is it synchronized?
Yes, it's okay. Yes, we can see it. Just let me see.
Oh, good. Now, if you see at the same time, now there is okay.
We can see only, yeah. Okay.
Now is equilibrium of cell gravitating systems.
Yes, we can see everything. My question,
okay, good.
We see your image twice, actually. Let's see your camera. Maybe we can take away one of them. I don't know how.
Ah.
Okay, now it's okay. Okay. Yeah.
Good.
It's
then
okay, just 5 minutes. Wait 5 minutes, and then we will be starting.
Yes, but is me which starts now?
Yes, yes.
Ah.
You will be
okay.
Announcing your talk, and then you start. Okay.
Okay, then I will stay with the slides
stay connected
on
for a while. Okay. Thank you.
Yeah. See you. Thank you.
Carlos, you hear me? Carlos, can you hear me? We're about to start.
Our speaker is on the microphone.
Speaker is remote. He's connected. He's connected, but apparently he's away moment. Let's see. He's not there. You see the webcam. He's not there. Apparently.
Oh wow!
Yes. But he was connected a moment ago. Yes. I think Okay, Carlos, can you hear us?
So let us start again. On the screen, we have Carlos Aguirre.
Hello?
Hello, you can hear us?
Yes, I can hear you well. I am here. Hello, everyone.
Perfect. You can see us as well?
Sorry?
You can see us as well?
I cannot see you. I am just because I am full.
Okay.
I am full screen, and let's see if I minimize, if I can see you. Ah, sorry, here.
And only for the later discussion, maybe. But now we can start, I think. And you will talk on a new channel for supermassive black hole formation. Carlos, it's on you.
Okay, thank you, everyone. Thank you. I would like to thank the organizers, Gregory, Remo, and all the people from Yerevan as well. And yes, today we'll talk about a new channel of supermassive black hole formation. This is the result of a paper we have recently published here, Welles, Boshkayev, Krut et al. In Monthly Notice last month. And this work was in collaboration with mainly with people from ICRANet, Remo Ruffini, Jorge Rueda, also people from Colombia, Edward Becerra and Uribe Suarez, and people from CONICET and La Plata National University of Argentina. This theory, the title, of course, it refers to supermassive black holes, but this talk will be framed on a broader theory of dark matter halo formation, as you will see. And therefore, in the first slides, I will talk about a few slides about the introduction of dark matter and which are the particles we are thinking of. So this is, as you see, a chronological picture, a schematic picture of the chronology of the universe from Big Bang to actual epochs. And the main objective of this talk will be assume that it exists beyond the standard model fermion, or spin 1/2 neutral fermion, which decouple after inflationary epoch and before CMB, decouple in a given regime from the plasma, and then start its evolution, is density evolution to form the pristine agglomerations of large-scale structure of dark matter halos, after which the baryons will fall inside the potential well of the dark matter and will start to form stars and the galaxies as we see today. So the challenge of this talk will be the first part to how to show how to form halos from these cell-gravitating fermions, and then how the supermassive black hole at the centers of that halo can arise from a mechanism related to dark matter. So I think I don't have to convince you that the success of dark matter, lambda CDM paradigm, from the cosmological perturbation theory, it can describe how primordial density perturbations grow into galactic structures. And then this can explain very well the CMB. As you can see in the picture from the right, the temperature power spectrum, if the dashed line represents the observations, this is an example to show that it is needed the dark matter as well as the dark energy. For example, this is an example that if you would put almost zero or very few dark matter into the energy momentum tensor, you cannot, the peaks, the second and third peaks of the temperature power spectrum will shift from the observations considerably. And if you put a lot of dark matter into the equations, it will also shift in order and will not fit the observations. Therefore, this is what after these few decades, people understood that this is one of the most compelling evidence for the existence of non-baryonic component in the mass energy momentum tensor of the Einstein equations. Of course, another probes of dark matter corresponds to the local universe, where you can see in the picture from the left distribution, the so-called cosmic web, how dark matter is distributed in the universe, which is not homogeneous, of course, is distributed in filaments, voids, and nodes. And this has been, can be recovered or as well reproduced by cosmological n-body simulations when put in terms of these called dark matter particles. And in the left, you can see a zoom into a node. This is a zoom from a simulation, where you can see, for example, at the scales of large halos into a large galaxy. And for example, when corresponding to these galaxies, in the bottom right picture, you can see the one of the most important probes of dark matter, which is the galaxy rotation curve, which it is needed a dark component extending the disk in order to explain the almost flat part of this rotation curve. Okay, now I will shift fast to dark matter halo formation from a statistical approach. So the first part of this talk will be based on how we can build dark matter halos from these cell-gravitating fermions. And after that, I will shift to the problem of supermassive black holes. So let's start with the collisionless relaxation. This is the equation you see here on the left, is the so-called Blasov-Poisson equation, which determines the evolution of the fine-grained phase space density of the particles. And for you to know, this equation is the master equation also used in cosmological n-body simulations, but it is used in a discretized manner to see how these phase space elements evolve and merge. But in this case, it can also be complementarily, it can also be attack this problem from a statistical approach, in which this Blasov-Poisson, which is Boltzmann coupled to gravity and with no collision in the right-hand side, can be rewritten by decomposing the fine-grained distribution function into a coarse grain plus fluctuations into this other equation. So this is a kind of a similar equation. This is a diffusion convection equation because it is an equation for the coarse grain distribution function, in which in the right-hand side you have this diffusion current when we have put all the fluctuations averaged in this member of the equation. And so, of course, this is a very difficult equation. One would like to solve a most likely coarse grain distribution function at relaxation. But this is a very difficult problem. But so this has been solved by imposing a maximum entropy production principle by Chabany in 1998, in which by asking to this diffusion current to maximize a coarse grain entropy, you can find the most likely stationary coarse grain phase space density of the particles, which, as you can see, is of Fermi-Dirac type. And this is, probably you remember, this solution is a generalization of the Linden-Bell distribution function of violent relaxation when including for escape of particles. In the numerator, for energies of the particle above the escape energy E sub m, you have no more particles in your system. So for fermions, if you like to describe these the particles as fermions, the maximum accessible value of this distribution function is fixed by Pauli principle, and therefore eta 0 here, the per factor, is proportional to the mass to the fourth, inverse proportional to the Planck h cube. Okay, so now once we have the most likely coarse-grained phase space density of these fermions at relaxation, we can start to build the equilibrium configurations. This is a very nice way to see how equilibrium equations arise from an extremization of entropy at statistical equilibrium. So you have the Fermi gas already at the statistical equilibrium, and you can try to solve the problem of the variational, first order variational principle of entropy. And so from this variational principle, you can, this is by alpha and beta global Lagrangian multipliers, and you can obtain by taking the variational equal to 0, the 3 equations you can recover from this principle. So the first is the Tolman-Oppenheimer-Volkoff equation. Of course, this is done in general relativity. The e to the lambda half is the spatial metric of the spherical symmetric space-time. And second equation is the Tolman condition for isothermality, and third equation is the Klein equation. So interestingly, by just asking an extremization of entropy, you can obtain this equilibrium equation. But this will be a first part of this talk, but a second part, which is where interesting things start to come up, is that when one try to understand as well the stability of the solutions. Stability, as you know, has to do with the second order variational of entropy. And in general relativity, this is quite a hard problem, but interestingly, it can be solved alternatively by just analyzing the topological properties of caloric curves. And I will show in a moment how by Katz, who was the first to realize about this point, I will show in a moment how it works. For a moment, we have the equilibrium equations, and now we will use the fact that fermions under self-gravity do admit a perfect fluid approximation. This was shown originally in the 1969 by the famous paper of Ruffini and Bonasola by solving Einstein-Dirac equations. And therefore, one directly have the system of equations. In the left, you can see the equation of a state, pressure and density, which are integrals of this coarse-grained phase space density of fermions that I showed before. And in the right-hand side, you can see the system, the coupled system. This is written in dimensionless manner, that's why it looks like that. But this is the equilibrium equation that I shown that can be derived from variational entropy principle, variational entropy as first order. So we have the Tolman-Oppenheimer-Volkoff, the Klein and Tolman condition, and also the energy conservation along geodesics. This theory is a 4 free parameter theory, that the effective temperature, which will be determined by parameter beta, the degeneracy parameter theta, and the cutoff parameter, and has to be solved as a boundary condition problem for the variables at the center of the configuration, which is here, written here down below. Okay, the most general solution of this equilibrium system of self-gravitating fermions in general relativity is the solution in continuous black line, you can see here. And interestingly, this has been done with boundary conditions corresponding to a typical spiral halos, meaning the halo scale length RH is of the order of 10 to the 4 parsecs, so 10 kiloparsec, with a mass at that scale of 10 to 11 solar masses. So interestingly, the outer part of the configuration, the fermions are in a dilute Boltzmannian-like regime, and therefore the profile resembles the typical dark matter profiles in the literature, for example, the NFW or INASTO. But these profiles, the INASTO and NFW are profiles which are determined from cosmological simulations, and the resolution is limited in that simulations, as you know, and below, let's say, some few kiloparsec, all these solutions are extrapolations. While the statistical and thermodynamic approach we are following allows, as we are solving differential equations, allow to provide a profile from the very center in a continuous manner, and you can see this rising part of density which is used with the fermions start to enter in a degenerate regime, and so therefore the pressure, the system is holding gravity due to the degeneracy pressure, and that's for you have like fermion, neutral fermion star or neutrino, stereo neutrino like star, with this very degenerate at the center, and which is surrounded by a dilute atmosphere, which the atmosphere, as you can see, can explain the halo of the galaxy. Therefore, you can check that this very dense core fulfills the quantum condition, because the thermal de Broglie wavelengths of the fermions at the core are larger than the interparticle mean distance. This can be demonstrated, that happens for degeneracy larger than 10. And interestingly, the different capacities of this core depends on the particle mass. So we have these core halo solutions. Now, let me discuss the stability, which is a very important problem to see, to understand this fermion gas in statistical equilibrium, which solutions are stable and which are not. So dynamical stability, which is having this phase space diffusion function, does not necessarily imply thermodynamic stability. And some dynamical stable solutions, which is having this F coarse-grained phase space solution of the Blasov, can be more likely to grow in nature than others. Therefore, I mean, to find both dynamically and thermodynamically stable solutions, one needs to solve this second variation principle problem, and to maximize this entropy. And therefore, we start with the global entropy, and which is an integral of the Gibbs-Duhem the entropy density with the volume, with the deep volume in spherical symmetry in general relativity. And one needs to solve, in order not to solve the second order variation of entropy analytically, one can solve it numerically by applying the Katz criterion. It relies on a derivative on the caloric curve. So we have energy. We have this is an example of the caloric curve. In the horizontal axis we have energy, and in the y-axis we have inverse of temperature, typical magnitudes of a caloric curve. And interestingly, the caloric curve can be built with all the equilibrium solutions. So each point of the caloric curve is an equilibrium solution of the equation. And interestingly, by applying the Katz criterion, this has been applied for a typical galaxy of 10 to the 10 solar masses, 510 to the 10 solar masses. But interestingly, the derivatives of the caloric curve defines the instability modes that the Fermi gas is achieving. And so from this caloric curve, you can see that, for example, the branch from B. So if you start with a solution of these gravitating fermions, the above part of the caloric curve, the fermions, it can be shown that are in a dilute regime. Well, here this enters the spiral. This is a small spiral, which it probably resembles to some of you the gravothermal catastrophe problem. But this has been historically solved for Maxwell, for Boltzmannian particles. When you solve for fermions, so when you have the Pauli principle, this spiral do not go to the singular isothermal sphere, but derolls, and because of its halt, the gravothermal catastrophe by the Pauli principle. This was demonstrated by Chavani in the 90s and later on. And interestingly, you start to have new solutions, which are the ones that I will show now next, lies in this stable branch. So it appears that there is a stable branch of between B and C in blue. So in purple, you have the unstable solution, while in blue you have a stable. And other important point of this caloric curve is that I will show you can have core halo distribution of fermions, which are stable, and the point C of this caloric curve is the last stable configuration that I will show in a moment. Interestingly, last stable configuration has been historically been shown by the onset of thermodynamic stability at a turning point. So through the so-called dm d rho, the derivative of the total mass respect to the central density. So to find maximum in this curve. So if from this caloric curve, instead of following all these solutions in terms of the total mass and central density, you can demonstrate that it exists a turning point, indeed, and that all the unstable solution will be necessarily be unstable to the right of the turning point, while interestingly to the left, you can still have unstable solutions, because this theorem of turning point don't provide a necessary condition for instability, only a sufficient condition. And interestingly, when fermions are at finite temperature, you can demonstrate that the last stable solution is at the minimum of this plot, and at this minimum, when the total mass is at this minimum, the core mass of this core halo distribution is at this maximum, and you have the so-called core collapse. Therefore, I will repeat this again. So this caloric curve, you can find a stable solution of these fermions, but at point C, you have, therefore in the microcanonical, you have a fixed energy. You have no other accessible state at this fixed energy at point C, and therefore this is a turnover. This solution C is the last stable one, which corresponds to this minimum in this curve, and the core of the configuration will necessarily go to a black hole. I will, okay, this is a slide showing that how you can calculate, how you can show that the profiles, that the core halo profiles of these fermions corresponds, are in a cosmological framework, meaning once starting from these fermions of tens of keV, you can solve the power spectrum of the fermion and then apply the Press-Schechter formalism. This is just to show that from Press-Schechter and using the mass variance, you can obtain a given boundary condition. So this is the virial radius and the mass scale of the halos that you can obtain from a linear structure formation theory using this, for example, a class algorithm. And therefore, for example, we choose here a given mass, virial mass of 510 to the 10, and then we have to find all the equilibrium solution for this boundary condition mass. And here there are examples. For example, of a mass of 50 keV. Here are examples of these different kind of profiles of fermions you can obtain for exactly at this fixed virial mass. You can have solutions like 3, which are in purple, which is the core halo, and solutions like 2, which are very similar in dotted, which are core halo but are unstable. So this solution corresponds to this point here in the caloric curve, 2 and 3. This is just an example where solution 2 is very similar to 3, but is unstable thermodynamically because it lies on the upper part of this turnover in the caloric curve, while 3 is similar, but is thermodynamically stable. Okay, so here I have shown how you can find equilibrium solution of fermions in a core halo regime and to be stable. Now we will move to the main result of this talk, which is a new challenge for supermassive black hole formation. So we have recently extended these calculations to virial masses from 10 to 10 to 10 to 12 solar masses, and build for an example of a particle mass of 100 keV. And therefore, we have systematically calculated the critical solutions of this core halo So point C, this last stable solution in the caloric curves, point C1, C2, and C3 here in bottom are assumed of this lower part of the caloric curves. And two important things to say from this plot. So the larger the total halo mass, the smaller is the stable branch of these core halo solutions. You can see here in blue, we have a quite extended stable branch with many different core halo solutions. For 10 to 11, the stable branch is shorter, and for 10 to 12, it just has disappeared, the stable branch. This is a very first important result, which is this theory is telling us that you should not observe galaxies, individual halos of galaxies of order of magnitude above 10 to 12. And this is interesting correspondence to what we see in the universe, because clusters, large galaxies are about up to order 10 to 12, and from 10 to 13, 14, we start to have a cluster of galaxies with merging processes. And this is showing how powerful is the thermodynamics of self-gravitating fermions, showing the maximum mass of a given system, the stable system. And interestingly, now we can wonder which is the mass, the critical mass of the core at this last stable configuration, C1. And this is what I have shown here. So in the picture of the left, I showed 3 examples of core halo profiles lying at the last stable configuration, where the core for turning point criterion or for the caloric criterion is critical. For this 100 keV example, the critical mass of the core is ordered 6 times 10 to the 7 solar masses, so typical masses of active galaxies. And this critical mass of the core is surrounded by a diluted halo, which we have checked in the picture on the right, that these points C1, C2, and C3 lies, the halos of these solutions lies within an observable dark matter surface density relation, because as you can see, the halos here in the picture on the left, so the more extended the halo, the somewhat lower is the inner halo density here at the plateau. This is exactly what needs to be. So smaller galaxies are somewhat denser towards the inner halo regions, while larger galaxies are more diluted. This goes as has been checked as observationally confirmed by the so-called dark matter surface density relation, or sometimes the Donato relation, which is a product of the. Here there is an equal, which is not near printed, but is proportional to the inner halo density times the R naught, or 1 halo scaling. So this is the main result of this theory, which is showing that it exists a solution of Einstein equations for self-gravitating system of fermions, which can explain the mass of the dark matter particles, because for 100 keV, we can have the 100 keV is a typical mass which goes perfectly well with the large-scale structure of the universe. In cosmology, then the formation of supermassive black hole at the center of active galaxies, because we have shown that this critical mass corresponds to the last stable configuration thermodynamically demonstrated in general relativity, and the phenomenology and stability of halos, because the surrounding halo, which is surrounding this critical core, fulfills with the observational relation. In this recently published work, we have as well followed the further evolution of this black hole seed by computing a Kerr metric, because even if we started with a spherical symmetric stationary spacetime, once it starts to accrete from a disk, surrounding disk, we use a geodesic disk in general relativity, it starts to gain angular momentum, and the system will start to rotate, and therefore, for consistency, you have to solve the problem in a Kerr metric. So this has been done in a collaboration in this last work where we have shown that the black hole, by asking the analogous to the Eddington balance, we have asked local balance between gravitational acceleration and radiation pressure along the z-axis, because it is actually symmetric thing, not spherically, for the disk. And so in the picture here of the bottom, you can see the mass of the seed growing as a function of time. One is gaining mass and angular momentum from the surrounding baryonic disk. And here we have shown that, for example, starting at redshift corresponding to the form halo at high redshift, which from the projector we determine, like, for example, at 3 sigma at redshift around 7, you can start with a virial form halo of about 10 to 11 solar masses, and the core, which is 10 to 7, the seed, this black hole seed, start to grow. And you can see that, for example, if we see at efficiencies for a seed, as I have shown here, 6 10 to the 7, so the dashed line for 100 keV of particles, the central mass can grow, for example, up to 10 to 10 solar masses, the black hole, in the first half of GI year of the life of the universe. And this is an important result in terms of this theory, because it is saying that the black hole seeds, which are considerably larger than baryonic seeds, for example, you have heard about population 3 star black hole formation channel, but it leads to black hole seeds of order of 10 to 3, 10 to 2 solar masses, which then have hard times to grow until 10 to 9 in the first fraction of the life of the universe. And in this case, this theory of dark matter cores, which are from core collapse, it is possible, it is totally possible to grow these black holes up to values observed in high redshift quasars in the universe. And well, the last part of the talk is to show that for the same particle mass of 100 keV in this case, as an example, we can, instead of being at the last stable configuration, we can have solutions which are below critical, so which are core halo nature, but below critical. And we can see that it is very interesting that it can apply, for example, to non-active galaxies like our own. Let me show fast the rotation curve of the Milky Way. This is in the picture of the bottom, the rotation curve of the Milky Way in linear and in logarithmic in the left. And we will use this data and to test our model of fermions, and we will also use S star from the star cluster, where, as you probably know, the S2 star, which is one of the closest of the galaxy center, puts the best constraint to the mass of the central object, which is 4 million solar masses. Therefore, by applying these non-critical core halo solutions, we ask if the gravitational potential of this solution can explain the Milky Way rotation curve together with the S-star dynamics, but without the singularity, just the core, this very compact core of dark matter. And then, interestingly, we have shown in a few years ago that there is a family of solutions. So for fixed boundary conditions, which fulfills the rotation curve, as you can see in red, the rotation curve of the Milky Way, at the center, given that these fermions are very degenerate, it can also explain, for example, for particle masses that goes from 50 up to 300 keV, so 100 keV is a typical solution here, is compact enough, the core, in order to explain the motion of the S stars, which are these small blue stars in the rotation curve. And but 100 keV is a solution here, which is below critical, because the temperature, the central temperature of this configuration is such that the core is compact enough to be inside the pericenter of the stars, and therefore explain their dynamics, but not yet collapsed. And this is very interesting. We have further recently with a PhD student in Argentina here in the high performance compute center in Cordoba. We have calculated by Monte Carlo the best fit of the orbital parameters of the S2 star. Here in the rare model, where the central object is a dark matter quantum core of 100 keV, you can see how good can explain the astrometric position of the orbit in the sky. And in the picture of the right, you can see the result from the gravity collaboration, where the orbital elements all are basically the same at the first and second digit precision. And this the posterior of the parameters with this Monte Carlo method for 100 keV, where we can see that the best fits of the orbital parameters, eccentricity, semi-major axis, and so on, are statistically equivalent to the ones determined by the Schwarzschild black hole. Okay, so I will put the discussion on my last slide, just to discuss that how our framework will be now placed in the different channels of black hole formation. This is a slide from Volonteri et al. 2021, when in this plot you can see in the y-axis the number density of observed black holes in the universe, and in the x-axis the mass of the central object of the black holes in this case. And you can see that in the shadowed light blue region here, you can have the solar mass black holes. Then you have this famous gap between the massive black holes in gray, in shadowed gray, where you have this couple of examples of gravitational waves, where it indicates the existence of filling partially this gap between the solar mass black holes and the massive black holes. And this schematically in this plot, in the squares, you have the different mechanisms known or proposed up to now for massive black hole formation. So you have the three different channels. So baryonic channels, for example, population 3 stars, which are stars which are born in the early universe, with no heavy elements, just hydrogen, which then can collapse to form remnants of order 10 to 2 solar masses around. Then direct collapse of gas clouds. So this is a bit a different mechanism where you assume that this halo of 10 to 8, let's say, solar masses in the early universe, and somehow this by different reasons, this galaxy, if this galaxy could not form stars, the gas which is there will direct collapse to a very massive star, which can end in a remnant of order 10 to 4, 10 to 5 solar masses. So these are larger remnants. And by the way, actually, within the paradigm of simulations, this direct collapse of gas are among the preferred mechanisms for forming halos. Then you have a runaway collision star in clusters, and then you have other channels, more hypothetical, which are early universe channels, which are really purely constrained because the epoch at which these typical channels arise are from topological defects coming from inflationary epochs, so like cosmic domain walls. And then here is a channel that we are proposing now, which is dark matter channels, meaning the dark matter halos as they form, as I have shown, when considering the Pauli principle, the quantum nature of the particles, which cannot be accounted for in traditional n-body simulations, can have these core concentrations, which can collapse, make core collapse, as we have shown here from thermodynamics. For example, in this that I have added in the yellow line, a critical mass of 10 to 7 solar masses, so will form a seed black hole of 10 to 7, while this theory of dark matter is suggesting that lower to this 10 to 7, for example, it can exist very dense cores of dark matter not yet collapsed, and therefore, but still that you can explain the phenomenology of Sagittarius A star, as I have shown. And after that, for masses above 10 to 7, for typical active galaxies like M87, our framework can show that how these seeds can grow in the past to provide larger black holes. And then there are one more dark matter channel of formation, which invokes for self-interaction. This is reminiscent from Wahlberg and Shapiro, all their ideas, but we can provide this channel without self-interaction just by including the Pauli principle. Okay, and I will leave you here with this last slide of discussion, and I thank you all for the attention. You have any questions?
Thank you, Carlos. There might be questions. Let me add, there are two ladies first, maybe. Go ahead, take a microphone that can understand you.
Thank you for this interesting talk. I was wondering whether this core collapse depends on the rotation. If you were to increase rotation into the seeds, wouldn't this change then? And would it still be fitting with the phenomenology like such a star?
Thank you for the question. I only listen partially because maybe the mic is a bit far from the audience. Maybe some of the organizer can repeat the question louder, please. Or...
Next question?
Yeah. Hi, Carlos. What are you doing in this code?
No, sorry, I cannot hear you. I can hear very low. Sorry. Can you please repeat it louder?
Maybe if you come closer to the or you stay here, then or if you stay just here, you can stay closer.
Otherwise,
I will repeat my questions over there.
So, Carlos, can you hear me?
I can hear you better now. Narek, is you?
Okay, now there will be the question. They will repeat the question, yes?
Yeah.
Yes, thank you.
Yeah, okay, so once more, thanks again for this interesting talk. And I've been wondering whether rotation would make a difference for the core collapse. So when your seed, your core would be rotating, did you study whether it makes some difference, it would collapse at some other point? And would this be consistent with phenomenology, let's say, for such a star?
Yes. Yes, thank you. Very nice question. Well, up to now, as you know, halos, as they born, the overall rotation they have is quite negligible. Therefore, that's why when generally build the halos of dark matter without rotation. Now, in this example, but in any case, one could generalize these equations with rotation. So one could start with the distribution function that I showed in the beginning of fermions with some angular momentum of the particles, and then we will have we can have a rotation. But the rotation we included in this last paper only once this black hole seed is formed to calculate the accretion. The interesting question whether if the critical mass of collapse, how it will depend on the rotation of the dark matter core, we didn't study, but this, considering that the fermions are in the highly degenerate regime, this should resemble the theory of, for example, neutron star, the critical mass of a neutron star, because in the end, this is a self-gravitating system of fermions, like neutrons, but in this case are stellar neutrino-like instead of neutrons. But there are the known effects of neutron star when you consider rotation, how the critical mass shifts, and I think this work can be done, but we have not pursued yet in our theory. Just when collapsing, but not prior to that.
Okay, now the next question.
Yes. Hi, Carlos.
Hi, Felix.
My question is, I have two questions. First, what are the, or could be the observational tests to differentiate between these different models for the seeds of these supermassive black holes? This is the first question. And the second is, what accretion rate you consider not reasonable?
Okay. Yes. Yes. Well, I will start from the second question. So we have considered here, yes, we have here considered in this equation. This equation is the local balance between gravitational acceleration and radiation pressure. But for this beta is a coefficient which is from 0 to 1, and this implies that this is the analogous of the efficiency in the accretion, and we have only considered below critical accretion. So what will be the analogous of below Eddington accretion limited? What I usually don't like, or I always see that as a fine tuning, where people need to go to super Eddington or hyper Eddington accretion limit and tune this accretion depending on the age of the universe, in order for example, a small seed can grow that large to, let's say, 10 to 9. So that's why we have limited to use standard accretion regimes. Though I am not an expert of accretion, so I would say I cannot judge which are the problems with super Eddington or hyper Eddington accretion. I know people use it because of convenience to reach final masses, but okay, this is my impression to this. And the first question is very interesting: is which are the observational different possible ways of constraining these different massive black hole formation channels? Well,
yes, it's essentially how observationally we could discriminate between these different proposed channels.
Yes, this is a very nice question. This is difficult. This is difficult to answer because, for example, the case, well, all channels depends on different hypotheses. For example, for baryonic channels, one should check for observational signatures of these population 3 stars, if it exists or not, because are still hypothetical. These stars formed mainly by hydrogen. This is, for example, with the new telescopes, people is trying to see some signatures of these large stars, but still no confirmation. Then, well, early universe I will not say, because it's very hypothetical. It is there are no yet observational signature of a topological defect, nor the cosmic string, nor domain walls, and what I can say, at least from our theory, is that there are observational proofs of our theory, or at least potentially, because our theory implies that central objects below critical will not be black holes, will be very compact. but not black holes. And therefore, it has different consequences. We have, for example, one consequence is the precession. If you have enough resolution, observational resolution, the precession of a star which is orbiting the central object the precession will be different if you have a singularity or a central mass, punctual mass, or if you have a distribution. This is one point. Second point is the shadow. The shadow of how lights curve in the center, it can only be tested if you have a singularity or if you have a distribution. We have pursuing this work by doing the ray tracing and showing that you can also form shadows by compacting object. Indeed, I have a couple of slides about this. This is a work, a very nice work we are about to finish, showing that by this core halo distribution, you can produce shadows, a ring-like structure for light without having a black hole. And this is another way to observational distinguish our paradigm with respect to the black hole paradigm.
Okay.
Well, thank you.
There's a very last question. And I hope for a short answer. Because
okay, so hello. My question is rather than being focused on the formation of black holes, is focused on just the model of structure formation itself. And I'm just wondering whether this model can form bigger structure earlier compared to the standard scenario where you form small structures and then you merge them and you form bigger ones. So I'm just wondering whether this process through fermionic dark matter core collapse can speed up structure formation. My question is related to the claim by the James Webb telescope to have observed supermassive galaxies like 10 to 11 solar masses with an age less than 1 gigayears. This would be a disaster for the standard dark matter scenario. So we need a model that speeds up structure formation if it is confirmed, this observation is confirmed. So
yes, this is a very interesting question. I know that the James Webb is not only observing massive black holes in high redshift, but also halos or small halos. Of course, as far as I understand, the quality of the image are not totally conclusive as yet.
Okay, is it interrupted now?
It's frozen.
It's frozen now. Okay, but
okay, that's
maybe you can clarify is still on? No, it's frozen. The picture, the connection is interrupted at the moment. Can you check? Is there someone who can help us? Connection, I don't know. So, how much I know is his connection, not our. Okay, then we have to so many kilometers out of you know that's not a problem. Okay, this way.
Hello.
He's back. Okay. Here, please finish.
So, there was a problem with the connection. Now I am back. Sorry.
Your question becomes answered.
Okay, sorry.
Yes. So can you hear me?
Yes, we can hear you.
Yes. Okay. So I was yes. I think sorry. I will retake the last question. I think it's a very interesting question. Well, the formation scenario of halos in this framework of dark matter is totally analogous or similar to the standard formation scenario because we have done from the standard projector. When you start from the power spectrum of the mass power spectrum for this 100 capture, the only difference is that the 100 keV fermions is warmer than standard cold dark matter. Therefore, there may be some slight differences in the time of halo formation, but 100 keV is yet cold enough, right? Because typically warm particles are few keV, so this will not produce much differences regarding linear structure formation with respect to the traditional lambda CDM regarding the halos. The difference in our framework is due to when considered the quantum nature of the particles, where at the center of the halo it arises this quantum core. But so as far as I understand, the interesting thing of this paradigm of our core collapse, forming for core collapse, is that you will need much baryons in the early universe to form indeed you don't need baryons at all to form the black hole. This is first important point, because James Webb are observing halos where you have mainly no baryons. But the dark matter structure, I will say, is similar. The hierarchical structure formation is similar or analogous to the lambda CDM.
Okay, thank you, Carlo.
Yes. Yes.
And we close the session for today and meet again tomorrow morning, 9 o'clock. Is that right? Question to the organizers? Yeah, okay. Tomorrow morning, 9 o'clock. Thank you again to all speakers.
Thank you.
Sorry, we are seeing. I understand.